Hello, and welcome back to The Sleepy Astronomer. Tonight, we're going to witness something that sounds like it belongs in mythology rather than science. Two titans circling each other in the darkness, locked in a gravitational embrace neither can escape, falling toward each other across millions of light years with the patience of gods and the inevitability of physics. This is the story of the Milky Way and Andromeda, and the collision that will transform both of them into something neither would have become alone. If you joined me recently to discover how big Andromeda really is, welcome back to continue that journey. We learned something unsettling together, that our nearest large galactic neighbour isn't quite as separate as we thought, that its dark matter halo already reaches across space and touches us, that we're living inside an overlap zone where the boundaries between galaxies have already begun to dissolve. And if you're settling in for the first time tonight, welcome aboard this cosmic voyage. What we're about to explore together is one of the most spectacular events in our universe's future, and one of the strangest stories about what happens when giants meet in the dark. Wherever you are tonight, settling in for rest or simply curious about the slow-motion catastrophe unfolding in the space around us, I'm so glad you're here. If this journey through the Great Galactic Showdown helps you unwind or fills you with that particular kind of cosmic wonder that comes from watching inevitable forces play out across unimaginable timescales, feel free to give the video a like. And if you'd like to help other space enthusiasts discover these peaceful astronomical journeys, a subscription really does help the channel reach fellow dreamers looking for calming content to drift off to. It means the universe to me, and it helps build this wonderful community of curious minds and starlight admirers. So, find your most comfortable position and let's begin, because tonight we're going to watch two galaxies prepare for an encounter that will span billions of years, an event so vast and so slow that calling it a collision almost seems wrong. It's more like a merger, a transformation, two separate entities becoming one through a process so patient and so inevitable that it makes human history look like a single heartbeat. The story starts with a question that seems simple on the surface. What happens when two galaxies collide? You might imagine chaos, stars smashing into each other, planets destroyed, solar systems obliterated in cosmic violence. And while there will be spectacular fireworks, the reality is stranger and more subtle than simple destruction. Because galaxies are mostly empty space, and the collision between them is less like two solid objects crashing together and more like two clouds slowly interpenetrating, their particles passing through each other, while gravity orchestrates a dance that will last longer than our species has existed. But this isn't just any collision. This is personal. These are our galaxies, the Milky Way, our cosmic home, and Andromeda, our nearest large neighbour. For decades, astronomers have studied what will happen when they finally meet. They've run computer simulations, traced orbital paths, calculated energies and timescales. They've given the resulting merged galaxy a name, Milkomeda, or sometimes Milkdromeda, as if naming it could make the transformation feel more comfortable, more manageable, less like the end of everything we know. Because here's what makes this collision different from all the other galaxy mergers we observe across the universe. Those distant collisions are just beautiful phenomena to study, cosmic events happening to objects so far away they might as well be abstractions. But this collision involves us, our sun, our solar system, our galaxy. Everything we can see when we look up at the night sky will be part of this merger. We have front-row seats to an event that will reshape our cosmic neighborhood, and while we won't be around to see the finale, the opening act has already begun. We know how it ends. The simulations are clear. In roughly 4 to 6 billion years, the Milky Way and Andromeda will have completely merged into a single massive elliptical galaxy. Both spiral structures will be destroyed. Both identities will be erased. The beautiful arms of stars that currently define both galaxies will be torn apart and scattered. The organized rotation will dissolve into chaos, and what emerges will be something entirely new, larger than either galaxy alone, but also fundamentally different in character. And here's the question that haunts this entire story. Which galaxy wins? When two titans meet, surely one must dominate. One must be the victor, the survivor, the galaxy that imposes its will on the other. That's how we think about conflicts, isn't it? There's always a winner and a loser, a dominant force and a conquered one. But the universe doesn't work that way. Gravity doesn't recognize the concept of winning. What we're about to discover is that this collision has no winners, only two participants in a transformation neither can avoid, both equally doomed, both equally necessary for what comes next. The ancient Greeks told a story about Andromeda, the chained princess waiting to be rescued from a sea monster. Perseus came to save her, killed the beast, won her hand in marriage. It's a story about heroes and rescue and triumph over chaos. But the real Andromeda, that faint smudge of light in our autumn sky, needs no saving. Neither do we. What's happening between our galaxies isn't rescue or conquest. It's something more like destiny, written in the mathematics of gravity and the initial conditions of the universe, playing out with the inevitability of water flowing downhill. Tonight, we're going to meet both combatants properly, understand what each galaxy brings to this encounter, measure their strengths and weaknesses, like preparing a fighter's profile before a championship bout. We'll examine the gravitational trap that binds them together, the physics that makes escape impossible, the orbital mechanics that dictate how and when they'll meet. We'll watch the approach begin, see the first dramatic contact, witness the repeated passes as both galaxies swing around each other in a spiral dance that gradually tightens with each revolution. And we'll be there for the finale, when the supermassive black holes at each galaxy's heart finally merge, when the last remnants of spiral structure dissolve, when Milkomeda is born from the wreckage of two once beautiful galaxies. But here's what makes this story worth telling as you drift towards sleep. Despite all the violence and transformation, despite the complete destruction of both galaxies as separate entities, almost nothing dies. Stars don't collide, space is too empty for that. Our sun, if it still exists when the merger happens, will probably pass through the entire event without coming close to another star. The destruction is structural, not physical. It's the death of form, not substance, the end of organization, not existence. There's something almost meditative about that, don't you think? The idea that you can be completely transformed, have your entire structure dissolved and reformed, and yet somehow continue. That endings and beginnings can blur together. That loss of identity doesn't mean annihilation. So, settle in, get comfortable, and let's watch two titans prepare for their slow dance in the dark, knowing from the start that neither will survive as they are, but that what they become together might be more magnificent than either was alone. This is a story about inevitability, about surrender to forces larger than ourselves, about what happens when you stop asking who wins and start accepting that some transformations have no victors, only participants in something vast and patient and utterly beyond our power to prevent or understand. The collision is coming, has been coming for billions of years, will continue coming for billions more, and tonight we're going to watch it unfold. Before any great contest, there's a moment of introduction. The fighters stand in their corners while someone with a microphone reads their statistics. Height, weight, reach, record. It's a ritual we perform before boxing matches and cosmic collisions alike. This careful cataloguing of strengths and weaknesses, this weighing and measuring of opponents. We do it because we want to know what we're about to witness. We want to understand the forces about to collide. So let's meet our contenders properly. In one corner, we have the Milky Way, our home galaxy, the only one we've ever known from the inside, the cosmic neighborhood that contains everything humans have ever seen with the naked eye except for Andromeda itself and the Magellanic Clouds. In the other corner, Andromeda, the great spiral in the autumn sky, our nearest large galactic neighbor, the galaxy that's been approaching us for billions of years with the patience of deep time and the inevitability of gravity. The comparison matters because we've spent decades wondering which galaxy would dominate this encounter. We've run the numbers, built the simulations, analysed the data with the careful attention of gamblers studying odds. And what we've discovered is both surprising and strangely poetic. They're almost perfectly matched. Two titans of roughly equal mass approaching each other through the darkness, neither with a decisive advantage. It's the kind of cosmic coincidence that makes you wonder if the universe has a sense of dramatic timing. Let's start with home. The Milky Way is a barred spiral galaxy. Barred meaning it has a rectangular structure of stars running through its center, with the spiral arms emerging from the ends of that bar rather than from a central point. If you could somehow step outside our galaxy and view it from above, you'd see something magnificent. A broad disk of stars about 100,000 light-years across, maybe a bit more depending on where you decide the edge really is. 4 major spiral arms wind outward from that central bar, each arm packed with young blue stars, glowing gas clouds, and the kind of active star formation that makes spiral galaxies so photogenic. The structure is elegant in its organisation. At the very centre sits the bulge, a dense, roughly spherical collection of old stars that gives the galaxy its 3-dimensional depth. Buried within that bulge, invisible except through its gravitational effects and the occasional burst of radiation, when something falls into it, lurks Sagittarius, a star. That's our supermassive black hole weighing in at about 4 million times the mass of the Sun. It sounds enormous, and by human standards it certainly is, but in galactic terms it's actually rather modest. We'll get to why that matters in a moment. The disk is where most of the action happens, where gas clouds collapse to form new stars, where supernovae explode and seed space with heavy elements, where the spiral arms rotate through space like a cosmic pinwheel. Our Sun lives in the disk, about 26,000 light-years from the galactic centre, orbiting the galaxy once every 230 million years or so. The dinosaurs were just beginning their reign the last time we were in this position in our orbit. By the time we complete another lap, who knows what or who will be watching the stars from Earth. Beyond the visible disk lies the halo, that sparse spherical cloud of old stars and globular clusters we discovered when we realized the galaxy extended far beyond the bright spiral arms. These are ancient stars, among the oldest in the galaxy, drifting in elliptical orbits that take them high above and below the plane of the disk. And beyond even that lies the dark matter halo, that vast, invisible structure containing most of the galaxy's mass, reaching perhaps 2 million light-years from the galactic centre in all directions. We talked about that halo in our last journey together, how it extends so far that it already overlaps with Andromeda's halo. That overlap is the beginning of the merger, the opening move in a game of cosmic chess that will last billions of years. How massive is the Milky Way when you add up all that visible matter and invisible dark matter? The latest estimates put us at around 1 trillion times the mass of the Sun. Maybe a bit less, maybe a bit more. The uncertainty is still significant, especially when you're trying to measure something as diffuse and extended as a dark matter halo. But 1 trillion solar masses is a good working number, the kind of mass that gives us significant gravitational authority in our cosmic neighborhood. How many stars call the Milky Way home? This is surprisingly hard to answer. Counting stars in a galaxy you're inside is like trying to count trees in a forest when you're standing among them. You can see some clearly, others are hidden behind the ones in front, and the ones far away blur together into a general glow. Best estimates suggest somewhere between 200 and 400 billion stars, possibly more if the halo contains large populations of dim red dwarfs we haven't detected yet. Some of those stars are massive blue giants burning bright and dying young. Others are tiny red dwarfs barely glowing, capable of lasting trillions of years. The Sun sits comfortably in the middle, neither unusually large nor unusually small, neither particularly bright nor particularly dim. We're average, which in galactic terms is actually quite fortunate. Average stars live long, stable lives, the kind of lives that give planets time to develop interesting chemistry and perhaps even biology. So that's the home team, the Milky Way, our cosmic champion, a beautiful barred spiral containing 1 trillion solar masses, hundreds of billions of stars, active star formation in the spiral arms, a modest supermassive black hole at the center, and a vast, dark matter halo reaching far into the space around us. We've got a solid structure, good organization, healthy star formation. We're in our prime, cosmically speaking. Now let's meet the challenger. Andromeda, designated M31 in astronomical catalogues, the 31st entry in Charles Messier's list of things that weren't the comets he was hunting for, has been our closest large galactic neighbour for as long as both galaxies have existed. It's a grand spiral galaxy, though its spiral structure is perhaps a bit less organised than ours, its arms a bit more fragmented and chaotic. Some astronomers describe it as transitional between a pure spiral and an elliptical galaxy, as if it's caught in the middle of some long transformation. That description will turn out to be more prophetic than the astronomers who wrote it probably intended. From Earth, Andromeda looks small, just that faint smudge in the autumn sky, barely visible to the naked eye. But that apparent size is deeply misleading. Andromeda is enormous. Its visible disk spans about 220,000 light-years from edge to edge, more than twice the diameter of the Milky Way's visible disk. If our eyes could see it at its true brightness, Andromeda would appear roughly 6 times wider than the full moon in our sky. We don't see it that way because most of its stars are too dim to register individually, and our eyes aren't designed to accumulate light over long exposures the way cameras can. But the size is there, hidden in plain sight, a massive spiral occupying a substantial chunk of sky that we mostly can't see. And just like the Milky Way, Andromeda's visible disk is just the beginning. It has its own stellar halo extending far beyond the spiral arms, its own dark matter halo reaching millions of light-years into space. That halo, as we learned in our previous journey, already touches ours. The contestants are already in contact, already feeling each other's gravitational influence, already beginning the slow dance that will eventually merge them into one. How massive is Andromeda? This was one of the great questions of 20th and early 21st century astronomy, the source of decades of debate and uncertainty. Early estimates varied wildly. Some suggested Andromeda was significantly more massive than the Milky Way. Others suggested they were roughly equal. The uncertainty came from the same problem that plagued measurements of our own galaxy. Most of the mass is in dark matter, and dark matter is extraordinarily difficult to measure. But the breakthrough measurements from Gaia and Hubble that we discussed in our last journey didn't just solve the puzzle for Andromeda. They gave us better measurements of the Milky Way's mass as well. And when the final numbers came in, they revealed something almost poetic. Andromeda and the Milky Way are nearly identical in mass. 1 to 1.5 trillion solar masses each, with Andromeda perhaps slightly more massive, but not by enough to make a decisive difference. We're equals. Peers, two galaxies of comparable weight approaching each other through the darkness. The number of stars in Andromeda is probably around 1 trillion, perhaps a bit fewer than in the Milky Way despite being slightly more massive. This apparent contradiction, more mass but fewer stars, tells us something about the composition of both galaxies. Andromeda likely has a higher proportion of low-mass red dwarf stars, or perhaps more dark matter relative to visible matter, or possibly both. The exact demographics are still being worked out, but the overall picture is clear. These are two large, mature spiral galaxies with similar stellar populations and similar structures. Now here's where the comparison gets interesting. Remember Sagittarius, a star, our supermassive black hole weighing 4 million solar masses? That's the black hole at the Milky Way's heart, the gravitational anchor around which everything in our galaxy ultimately orbits. It's massive by human standards, but in galactic terms, it's actually quite modest. Andromeda's supermassive black hole, designated M31, weighs somewhere between 100 and 200 million solar masses. That's 30 to 50 times more massive than ours. It's a monster by comparison, a gravitational beast lurking at the center of Andromeda's bulge, massive enough that when it eventually merges with our black hole billions of years from now, the resulting merged black hole will be almost entirely Andromeda's contribution. Our black hole will be little more than a rounding error in the final calculation. This disparity is puzzling, and it hints at something in Andromeda's history. Supermassive black holes grow by consuming matter and by merging with other black holes when galaxies collide. A black hole as massive as M31 suggests that Andromeda has been through mergers before, that it's already consumed smaller galaxies and absorbed their central black holes, and indeed there's evidence of this in Andromeda's structure. Look closely at Andromeda's central bulge in high-resolution images, not the faint smudge you see with your naked eye, and you'll notice something odd. The nucleus appears double, as if there are two bright concentrations of stars very close together rather than one. For years, this was called the double nucleus problem, a mystery that astronomers struggled to explain. The most likely solution, supported by computer simulations and observations, is that one of those bright spots is the remains of a smaller galaxy that Andromeda consumed in a merger perhaps a few 100 million years ago. The smaller galaxy's stars were absorbed into Andromeda's bulge, but they haven't completely mixed and spread out yet. We're seeing the remnants of a conquest, the scar tissue from a previous collision that hasn't quite healed. This means Andromeda has been through this before. It knows how to devour galaxies. It's done it recently enough that the evidence is still visible. Our Milky Way has also consumed smaller galaxies. The Sagittarius dwarf elliptical galaxy is being torn apart and absorbed right now, its stars becoming part of our galaxy's halo, but we haven't experienced a major merger with a galaxy of comparable size for billions of years. not since the Gaia-Enceladus collision roughly 10 billion years ago, an ancient event we can only reconstruct through careful analysis of stellar ages and orbital patterns. So, you could argue that Andromeda has the experience advantage. It's fought this kind of battle more recently. It's still digesting the evidence of its last conquest, but experience doesn't matter much when gravity is the only force in play. Mergers aren't battles of skill or strategy, they're just mathematics, differential equations working themselves out over billions of years with patient inevitability. The ancient Babylonians told a story about Marduk and Tiamat, the young storm god facing the primordial dragon of chaos. Marduk defeats Tiamat and uses her body to create the cosmos, splitting her in half to form the heavens and the earth. It's a creation myth built on conflict, on the idea that order emerges from the defeat of chaos. The Norse had similar stories, Thor facing Jörmungandr, the world serpent, in a battle that would bring about Ragnarök, the end of everything. Conflict and creation intertwined, destruction and birth happening simultaneously. We tell these stories because we're drawn to conflict, to the clash of titans, to the spectacle of evenly matched opponents. We want to know who wins. We want to assign roles, hero and villain, victor and vanquished, the one who survives and the one who falls. It's deeply human, this need to frame everything as a competition with winners and losers. But galaxies don't care about our narratives. They don't have agency, don't make choices, don't fight or surrender or triumph. They just follow the mathematics of gravity, responding to forces that were set in motion billions of years ago when both galaxies first formed. The collision between Andromeda and the Milky Way isn't Marduk versus Tiamat or Thor versus the serpent. It's more like two clouds drifting together, two weather patterns merging into one, driven by forces that operate with absolute indifference to concepts like victory or defeat. And yet we can't help but ask, who wins? When two galaxies of nearly equal mass collide, which one survives? Which structure dominates? Which galaxy stars form the core of what emerges afterward? The uncomfortable answer, the one we'll explore more deeply as we trace the collision through its various stages, is that neither wins. Both lose their identity. Both are destroyed as separate entities. What emerges is something new, something that wasn't quite either galaxy, but contains pieces of both. Milkomeda won't be the Milky Way victorious over Andromeda. It won't be Andromeda absorbing the Milky Way. It'll be a new galaxy, a merger, a transformation that erases both identities in favour of something different. But we're getting ahead of ourselves. Right now, both galaxies still exist as separate entities. Both still maintain their structure, their organisation, their identity. The Milky Way spins peacefully, star formation proceeding in its spiral arms, our solar system orbiting on its 200 million year circuit around the galactic centre. Andromeda does the same, its own stars and solar systems living out their lives, completely unaware that anything unusual is happening. If you could somehow assemble both galaxies in a cosmic ring, have them face off in their corners while we read their statistics, the tail of the tape would show two remarkably evenly matched opponents, similar mass, similar size when you account for dark matter halos, similar stellar populations, both spiral galaxies in their prime, both with active star formation, both with vast dark matter halos extending far into space. Andromeda has the advantage in black hole mass and possibly recent merger experience. The Milky Way has the advantage in, well, actually, it's hard to identify a clear advantage. Maybe we're slightly more organised, our spiral structure a bit more pristine. Maybe our bar is a bit more prominent. But these are minor differences, cosmetic almost. What we have is two titans, perfectly matched, locked in a gravitational embrace neither can escape. And the most remarkable thing about this matchup is that it's happening right here, right now, involving us. Every other galaxy merger we observe is distant, abstract, something happening to objects so far away they're just data points in our telescopes. This one involves our home, our galaxy, our stars, our cosmic neighborhood. So there's your introduction to the contestants. Two roughly equal spiral galaxies, separated by just 2.537 million light-years of space, close enough that their dark matter halos already overlap, close enough that gravitational forces already bind them together, close enough that the outcome is no longer in doubt. They will collide, they will merge, and neither will survive the encounter as they are. The stage is set, the combatants have been introduced, the forces are already in motion. Now let's examine the trap they're caught in, the gravitational dynamics that make this collision not just likely, but absolutely inevitable, the mathematics that sealed their fate billions of years ago, when both galaxies first formed in the early universe. There's something beautifully ruthless about gravity. It never stops, never rests, never weakens in its resolve. It doesn't care whether you want to be pulled somewhere or not. It doesn't negotiate, doesn't compromise, doesn't offer escape clauses. Gravity is the universe's most patient predator, and once you're caught in its trap, the outcome becomes a matter of mathematics rather than hope. The Milky Way and Andromeda are caught in that trap together, and they have been for billions of years. Every second that passes, they fall toward each other a little bit faster. Every million years, they get a little bit closer. Every billion years, the gravitational binding between them grows stronger. There's no escape velocity they can reach, no trajectory that leads to freedom. The trap was set when both galaxies formed, and it will only close completely when both have merged into one. Let's talk about how that trap works and why it's absolutely inescapable. Isaac Newton gave us the key to understanding gravity more than 3 centuries ago, with an equation so simple it almost seems insulting that it could describe something as profound as the force holding the universe together. The force of gravity between two objects equals the gravitational constant times the product of their masses, divided by the square of the distance between them. F equals g times m, 1 times m2, divided by r squared. It's elegant in its simplicity, and absolutely unforgiving in its implications. What that equation tells us is that every object with mass attracts every other object with mass. Always. The attraction never stops, never reaches zero, never disappears completely no matter how far apart the objects are. The force gets weaker as distance increases. It drops off with the square of the distance, meaning if you double the distance, the force becomes 4 times weaker, but it never quite reaches zero. Put two objects anywhere in the universe, and they will pull on each other, however faintly. Now, when the objects in question are as massive as galaxies, and when they're separated by only a few million light-years, which is close in cosmic terms, closer than you'd expect evenly matched titans to be if they weren't already in each other's gravitational grip, the force becomes substantial, not strong enough that you could feel it if you were somehow floating in the space between both galaxies, not strong enough to overcome the local gravitational influence of nearby stars or the sun's hold on Earth, but strong enough that, integrated over billions of years, it pulls both galaxies into an inevitable collision. The question you might reasonably ask is, why can't they escape? The universe is expanding after all. We know this from Edwin Hubble's observations in the 1920s and countless studies since. Distant galaxies are receding from us, their light stretched toward the red end of the spectrum by the expansion of space itself. The farther away a galaxy is, the faster it appears to be moving away from us. Space itself is expanding, carrying galaxies apart like raisins in a rising loaf of bread. So why doesn't that expansion carry the Milky Way and Andromeda apart? Why doesn't it overwhelm the gravitational attraction and give both galaxies a reprieve from their fate? The answer is that gravity won. Past tense, it won billions of years ago, back when both galaxies were forming in the early universe. The expansion of space does indeed try to push galaxies apart, but gravity pulls them together, and which force wins depends on how close the galaxies are and how massive they are. For objects that are gravitationally bound, meaning their mutual attraction is stronger than the expansion of space, gravity always wins. And the Milky Way and Andromeda are very definitely gravitationally bound. We can calculate something called the binding energy of the system, which is a measure of how much energy you'd have to add to tear the two galaxies apart and let them escape each other's gravitational grip. For the Milky Way and Andromeda, that binding energy is enormous, something like 10 to the power of 56 joules, which is a number so large it loses all meaning. It's more energy than all the stars in both galaxies will produce over their entire lifetimes. There's no source of energy in our cosmic neighbourhood capable of providing that much oomph. The trap is closed, and it's been closed for a very long time. This binding isn't unique to our two galaxies. They're both part of something called the Local Group, a gravitationally bound cluster of more than 50 galaxies, most of them small dwarfs orbiting either the Milky Way or Andromeda like moons around planets. The whole Local Group is bound together, a small cosmic family held in place by mutual gravitational attraction, while the rest of the universe expands away from us. We're in a gravitational island, a pocket of space where the expansion of the universe has lost the battle against gravity's patient pull. Within the Local Group, the Milky Way and Andromeda are by far the dominant masses. We're the two giants, the two gravitational authorities that control the dynamics of everything else. The smaller galaxies, things like the Triangulum Galaxy, the Magellanic Clouds, the various dwarf spheroidals and irregular satellites, are all responding to our gravitational influence, following orbital paths dictated by the combined mass of the Milky Way and Andromeda. They're along for the ride, and when we eventually merge, they'll have to find new orbits around Milkomeda, or risk being absorbed into the merger themselves. Now let's talk about orbital mechanics, because understanding orbits is key to understanding why the collision is inevitable. When two objects orbit each other, whether they're planets around a star, moons around a planet, or galaxies around their common centre of mass, they're constantly falling toward each other, but they're also moving sideways fast enough that they keep missing. An orbit is essentially a continuous miss, a perpetual fall that never quite connects because the object keeps moving sideways fast enough to curve around the target instead of hitting it. For an orbit to be stable, the object needs to be moving at the right speed. Too slow, and it spirals inward and eventually collides. Too fast, and it reaches escape velocity and flies away forever. There's a perfect balance where the orbital speed is just right, and the object orbits indefinitely. The Milky Way and Andromeda had some orbital speed when they first formed. They weren't moving directly toward each other. There's some sideways motion, some angular momentum in the system that makes this more of a spiral approach than a head-on collision. If they had infinite time and no other forces acting on them, they might orbit each other forever, two galaxies locked in an eternal dance around their common centre of mass, never quite touching. But they don't have infinite time, and there are other forces acting on them. Specifically, there are tidal forces, those differential gravitational pulls that stretch objects in orbits, the same forces that raise ocean tides on Earth in response to the Moon's gravity. When two massive objects orbit each other closely enough, Tidal forces cause them to raise tides in each other, bulges of material pulled toward the other object. These tidal bulges contain mass, and that mass produces its own gravitational effects, which gradually slow down the orbital motion. It's a process called tidal friction, and while it operates very slowly, it's absolutely relentless. Every time the Milky Way and Andromeda swing around each other, and they've been doing this slow orbital dance for billions of years, they lose a little bit of orbital energy to tidal friction. The orbits decay very slowly, bringing them closer together with each pass. Eventually they'll get close enough that tidal forces become so strong they tear both galaxies apart, scattering stars and gas across space, while the central masses merge into one. The timeline for this process is billions of years, but the outcome is certain. And here's where dark matter makes everything worse, or more interesting, depending on your perspective. Remember those dark matter halos extending millions of light years around each galaxy? Those halos are already overlapping, already interpenetrating in the space between the visible galaxies. Dark matter doesn't collide like ordinary matter, doesn't create friction or heat or shock waves. It just flows through itself, particles passing through each other like two clouds of mist merging in the air. But dark matter has mass, and mass produces gravity, and gravity affects everything. The overlapping dark matter halos create a gravitational environment that's far more complex than just two-point masses attracting each other. There are density variations in the dark matter, regions where material from both halos is accumulated and regions where it's been pulled away. These variations create gravitational wakes and streams, subtle distortions in the gravitational field that affect how both galaxies orbit each other. Computer simulations, those patient calculations where astronomers model millions or billions of particles following gravitational laws forward through time, consistently show the same outcome. No matter what initial conditions you give the system, as long as the masses and distances are approximately what we observe, the galaxies collide. You can adjust the approach angle slightly, change the orbital velocities a bit, add or subtract dark matter from the halos. Doesn't matter. The binding energy is too large, the gravitational attraction too strong, the tidal friction too effective. Every simulation ends in merger, typically within 4 to 6 billion years from now. Some simulations show first contact happening a bit earlier, others a bit later. Some show a more direct approach, others show the galaxies swinging past each other once or twice before the final merger. But none, not one simulation run by any team of astronomers using any reasonable set of initial conditions, shows escape. The trap is mathematically inescapable. There's something almost philosophical about this degree of inevitability. The ancient Greeks had the Moirai, the three fates, who spun, measured, and cut the thread of every life. Clotho spun the thread, Lachesis measured it, and Atropos cut it when the time came. No one escaped the fates, not mortals, not heroes, not even gods in some tellings. Your fate was woven before you were born, and struggling against it was not only futile but often counterproductive, leading to the very doom you tried to avoid. The Norse had a similar concept of inevitable doom, though theirs were more violent. Ragnarök, the twilight of the gods, was prophesied from the beginning of creation. Odin knew how it would end, knew that he would fall in battle against the wolf Fenrir, knew that Thor would kill the world serpent Jörmungandr, but die from its poison, knew that fire would consume the world and that nearly everything would be destroyed. And yet the gods prepared for Ragnarök anyway, gathered heroes in Valhalla to fight in that final battle, went through the motions of preparation despite knowing the outcome was already written. The collision between the Milky Way and Andromeda is our own version of fate, and Ragnarok combined, a cosmic ending that was determined billions of years ago, written into the initial conditions of the universe, inescapable no matter what happens between now and then. The thread has been spun and measured, the doom is prophesied and approaching, and unlike the stories where heroes sometimes find loopholes or gods bargain for extensions, this ending has no loopholes. Physics doesn't negotiate. But here's the thing about cosmic determinism that makes it different from fatalism. There's no malice in it. The universe isn't punishing us. Gravity isn't cruel. The merger isn't happening because either galaxy did something wrong or because some cosmic judge decided this was appropriate. It's just mathematics playing out, differential equations reaching their inevitable solutions, potential energy converting to kinetic energy as both galaxies fall toward their common center of mass. There's actually something beautiful about it if you can step back far enough to see it. The collision was built into the structure of space-time from the moment both galaxies formed. Every particle in both galaxies has been following trajectories determined by the combined gravitational field, spiraling slowly inward through the fabric of space, participating in a cosmic choreography that will last longer than our species has existed and will continue long after we're gone. It's determined, yes, but it's determined by physics rather than by personality or choice or moral judgment. It's the universe being itself, following its own rules with perfect consistency. Ancient Hindu philosophy understood cosmic cycles in ways that modern cosmology is only now rediscovering. The universe in Hindu cosmology goes through endless cycles of creation and destruction, yugas within yugas, ages nested within ages, with creation emerging from destruction, and destruction eventually leading to new creation. Shiva is both destroyer and creator, the same deity responsible for endings and beginnings, because in cosmic terms there's no real distinction between the two. Every ending enables a new beginning. Every destruction clears space for new creation. The merger of the Milky Way and Andromeda fits that pattern perfectly. Yes, both galaxies will be destroyed as separate entities. Yes, the beautiful spiral structures will be torn apart. Yes, everything will be transformed beyond recognition, but the transformation isn't an ending. It's a transition. The stars don't disappear. They just end up in new orbits. The gas doesn't vanish. It gets shock-heated and eventually forms new stars. The black holes don't annihilate. They merge into a larger black hole. It's destruction and creation happening simultaneously, one process viewed from different angles. Why do humans find comfort in predetermined endings? Perhaps because knowing the future removes a certain kind of anxiety. If the outcome is certain, you don't have to worry about whether you're making the right choices or following the right path. The ending will arrive regardless, which frees you to focus on the journey rather than agonizing over the destination. There's peace in surrender, a kind of relief that comes from accepting something larger than yourself, something you can't control or change or escape. That's the lesson of the gravitational trap. The Milky Way and Andromeda can't escape each other. The collision is written into the physics, determined by the mass and distance and orbital parameters, guaranteed by the mathematics of gravity and the binding energy of the system. Struggling would be meaningless. Galaxies don't struggle, don't worry, don't try to escape. They just follow the trajectories that gravity prescribes, falling toward each other with perfect patience, allowing the universe to transform them according to its own inexorable rules. We've seen this happen elsewhere in the universe countless times. Everywhere we look with our telescopes, we see galaxies colliding, merging, transforming. The antennae galaxies, NGC 4038 and 4039, caught in mid-merger with long tidal tails of stars streaming into space. The mice galaxies, NGC 4676, two spirals locked in gravitational combat, their disks already distorted by mutual tidal forces. The tadpole galaxy, UGC 10214, with its enormous tail of stars stretching across space like a cosmic brushstroke. These aren't anomalies or rare events. This is how the universe builds large galaxies, through merger and accretion, through the slow gravitational consumption of smaller galaxies, and the dramatic collisions between comparable masses. Our collision is simply our turn in that endless cosmic cycle. The trap was set, the bait was taken, or rather, both galaxies were born already inside the trap, their fates sealed from the beginning, and now we're watching it close, slowly, patiently, with the inevitability of mathematics and the beauty of perfect physical law. The gravitational trap is inescapable, the ending is determined, and somehow, understanding that doesn't make it terrifying, it makes it almost peaceful. Because if you can't escape, if the outcome is certain, if physics has already written the final chapter, then all that's left is to watch it unfold, to appreciate the journey, to find meaning in the process, rather than anxiety about the conclusion. The trap is closed, the fall has begun, and there's a strange beauty in surrender, in accepting what the universe has already decided, in watching two titans tumble toward each other through the darkness with perfect patience and inevitable grace. Right now, at this very moment, the Milky Way and Andromeda are approaching each other at approximately 110 kilometers per second. That sounds fast, and by human standards it certainly is. It's about 300 times faster than a commercial airliner, fast enough to cross the United States in less than a minute. If you could somehow stand on the surface of the Milky Way and look toward Andromeda, you'd be closing the distance at a rate that would seem impressive by any terrestrial measure. But space is very, very large, and 110 kilometers per second, while fast by human standards, is agonizingly slow when measured against cosmic distances. At our current approach velocity, we're covering about 3.5 billion kilometers per year, roughly 23 times the distance from Earth to the Sun. That seems like a lot until you remember that we're currently separated by 2.537 million light-years, which is about 24 billion kilometers. Even travelling at more than 100 kilometers per second, it will take roughly 4 billion years before first contact, before the visible parts of both galaxies begin their dramatic interpenetration. 4 billion years. Let's sit with that number for a moment, because human minds aren't particularly good at comprehending timescales that vast. 4 billion years ago on Earth, there were no plants, no animals, no complex life of any kind. There was barely any oxygen in the atmosphere. The continents looked nothing like they do today. Life existed. Single-celled organisms had been around for a while, but it was still figuring out the basics, still experimenting with different approaches to survival. 4 billion years from now, assuming anything on Earth survives that long, the world will be as unrecognizable to us as that ancient Earth would be if we could somehow visit it. That's the timescale we're talking about for the approach. Not years or decades or centuries, not even millennia. Billions of years. Epochs so long that entire branches of the Tree of Life will rise and fall, continents will drift around the planet multiple times, stars will be born and die, and the sun itself will swell into a red giant and consume the inner planets. All of that will happen during the approach, during this slow gravitational waltz, as the Milky Way and Andromeda circle closer together. And yet, despite that incomprehensible slowness, the approach is happening. Right now. Every second we get 33 kilometers closer. Every year, 3.5 billion kilometers. every million years, a time span that still dwarfs human history but is barely a heartbeat in cosmic terms, we close the distance by 3.5 trillion kilometres, which is about 23,000 times the distance from Earth to the Sun. It's slow, but it's inexorable, and most importantly, it's not a straight line. If you imagined the collision as two objects hurtling directly at each other like cars on a head-on crash course, you'd be wrong. The approach is more complicated than that, more interesting, more dance-like. Because in addition to that 110 kilometers per second moving us closer together, there's also sideways motion, about 17 kilometers per second of transverse velocity, that makes this more of a spiral approach than a direct collision. Think of it like two figure skaters on ice, each skating in a wide circle, gradually spiraling inward toward each other, rather than charging straight ahead. The angular momentum in the system, that sideways motion, that rotational energy, means that Andromeda and the Milky Way will likely swing past each other on their first approach rather than colliding head-on. They'll get close, very close. Close enough that tidal forces will begin tearing at both galaxies' structures, but then they'll swing apart again, pulled back by their orbital energy before gravity drags them back together for another pass. It's the same principle that governs comets orbiting the Sun. A comet approaches from the outer solar system, swings around the Sun in a close pass, then heads back out again, unless it's on a trajectory that brings it so close that it either crashes into the Sun or gets disrupted by tidal forces. The Milky Way and Andromeda are following a similar pattern, just on a scale millions of times larger and with a timeline billions of times longer. Calculating the exact trajectory is remarkably difficult. You'd think with just two objects it would be straightforward. Just solve Newton's equations for two masses attracting each other gravitationally. But galaxies aren't point masses. They're extended objects with complex internal structures, and different parts of each galaxy feel different gravitational forces. The visible disk responds differently than the dark matter halo. The central bulge has its own dynamics. The spiral arms can be deformed and disrupted in ways that affect the overall mass distribution, which in turn affects the gravitational field, which affects the trajectory. And then there are all those smaller galaxies in the local group, adding their own gravitational influences to the system. The Triangulum Galaxy, M33, is the third largest galaxy in our neighbourhood, and while it's much smaller than either Andromeda or the Milky Way, it's massive enough to have its own gravitational effects. The Magellanic Clouds, orbiting the Milky Way, add their mass to our side of the equation. All of Andromeda's satellite galaxies contribute to its total gravitational pull. It's not a clean two-body problem. It's an n-body problem with dozens or hundreds of bodies, all affecting each other, all contributing to the final trajectory. This is why astronomers use computer simulations rather than trying to solve the equations analytically. You feed in the current positions, velocities, and masses of all the objects you care about. You let the computer calculate the gravitational forces between every object and every other object. You advance time forward by a small step, maybe 10,000 years, maybe 1,000,000, depending on how precise you need to be, and update all the positions and velocities based on those forces. Then you repeat billions of times, watching the simulation evolve forward through time until you see what happens. These simulations have been run hundreds of times by different research teams using different assumptions and different levels of detail, and while the specifics vary, the exact timing of first contact, the number of close passes before final merger, the precise shape of the tidal tails that get flung into space, the overall picture is consistent. First significant interaction happens in about 4 billion years. Complete merger takes another 2 billion years after that. The approach is slow, the collision is drawn out over multiple passes, and the result is Milkomeda. But let's focus on those first 2 billion years, the slow gathering of tension as both galaxies move closer together, as the gravitational forces between them strengthen, as the first signs of distortion begin to appear in their structures. For most of that time, very little will appear to be happening. Both galaxies will continue their normal operations. Stars will form in spiral arms. Old stars will die and return their matter to the interstellar medium. Planets will orbit their suns. Any civilizations that might exist in either galaxy will rise and fall without having any idea that a collision is approaching. Life, if it exists anywhere in either galaxy, will go on as normal because the timescales involved are so vast that changes happen far too slowly to notice within any creature's lifetime. The dark matter halos, already overlapping, will interpenetrate more deeply. The density of dark matter in the space between galaxies will gradually increase as matter from both halos flows into that region, creating stronger gravitational fields, accelerating the approach slightly. But dark matter doesn't do anything dramatic. It doesn't collide, doesn't heat up, doesn't produce light or shock waves. It just flows silently through itself, invisible and patient, setting up the gravitational architecture that will eventually tear both galaxies apart. The visible changes, when they finally begin, will start at the edges. Tidal forces, those differential gravitational pulls that stretch objects in orbits, will start to distort the outer regions of both galaxies first. Stars and gas clouds at the very edges of the Milky Way's disk will begin to feel Andromeda's pull more strongly than the center of our galaxy does, and that difference creates a stretching effect. Similarly, the edges of Andromeda's disk will begin to feel the Milky Way's gravitational influence, pulling them slightly in our direction. At first, these distortions will be subtle, detectable only in careful measurements of stellar positions and velocities. The beautiful spiral structures of both galaxies will remain intact. Their rotation curves will stay relatively normal. Their star formation will continue uninterrupted. But gradually, over hundreds of millions of years, the warping will become more pronounced. The disks will begin to tilt and twist. The outer spiral arms will start to deform, pulled by tidal forces into shapes that don't quite match the clean logarithmic spirals of an undisturbed galaxy. If anyone were watching from Earth during this period, and they won't be, because Earth will likely be uninhabitable long before this starts, consumed by the sun's expansion into a red giant phase, or at least rendered lifeless by the sun's increasing luminosity, they'd notice Andromeda growing larger in the sky. Right now, Andromeda's visible disk is about 6 times the apparent diameter of the full moon, though we can't see most of that with our naked eyes. In 1 billion years, it might appear 8 or 10 times the moon's diameter. In 2 billion years, it could span 30 or 40 moon widths, beginning to dominate the northern sky, no longer a faint smudge but a sprawling glow, bright enough that its structure would be visible to the naked eye. This is assuming you're watching from Earth's northern hemisphere, of course. From the southern hemisphere, Andromeda never rises very high above the horizon and might be less impressive. But for observers in the northern latitudes, the transformation of Andromeda from a faint patch to a massive celestial presence would be one of the most spectacular slow-motion changes ever visible in the night sky. The satellite galaxies, those small dwarf galaxies orbiting both Andromeda and the Milky Way, will be the first to feel dramatic effects. Caught between 2 gravitational giants, some of them will find their orbits destabilizing. A satellite that once orbited peacefully around one galaxy will suddenly find itself pulled equally by both, unable to maintain its original path. Some will be flung out into intergalactic space, ejected from the local group entirely by the complex gravitational dynamics. Others will fall into one galaxy or the other, torn apart by tidal forces and absorbed into the larger structure. M32 and M110, Andromeda's two largest satellites, are probably doomed. They orbit close enough to Andromeda that they'll be caught in the violence of the collision, disrupted and absorbed during the merger. The Magellanic Clouds, our own satellites, might survive if they're lucky, and if their orbits happen to keep them clear of the worst disruptions. Or they might be destroyed, pulled apart by tidal forces, or captured by Andromeda during a close pass. The simulations aren't precise enough to say for certain. The fate of small objects in a massive collision depends on exact positions at velocities at critical moments, and small changes in initial conditions can lead to wildly different outcomes. There's something poignant about those satellite galaxies, isn't there? They're small, insignificant compared to the giants whose orbits they follow, but they're still galaxies, still collections of millions or billions of stars, still structures that took billions of years to form. And there'll be collateral damage in a collision they have no control over, destroyed or ejected, simply because they happened to be nearby when two titans decided to merge. The ancient Greeks understood tragedy in ways that still resonate. Their plays weren't about good versus evil or heroes triumphing over villains. They were about people caught in circumstances beyond their control, watching as fate unfolded according to patterns they couldn't escape. Oedipus trying to avoid the prophecy that he'd kill his father and marry his mother, and thereby fulfilling it. Antigone choosing between divine law and human law, damned either way. The house of Atreus, generation after generation, cursed by the sins of their ancestors, unable to break free of the cycle of revenge and destruction. The collision between the Milky Way and Andromeda has that same quality of Greek tragedy, not because there's malice or punishment involved, but because there's inexorability. The approach was set in motion billions of years ago. The trajectory is determined by mathematics. The outcome is certain. And all the small players, the satellite galaxies, the solar systems, the planets, the potential civilizations, are caught in the gravitational drama of giants, unable to affect or escape what's coming. But here's where the cosmic perspective offers something that Greek tragedy usually doesn't: distance and beauty. We're not personally invested in this collision. We won't be here to experience it. Our species will be gone. Our sun will be dead or dying. Earth will be uninhabitable or consumed. We're watching from a position of perfect safety, separated from the event by billions of years, able to appreciate it as spectacle rather than suffering through it as participants. This is the privilege of cosmological knowledge, the ability to witness events we'll never experience, to understand futures we'll never inhabit, to trace the destinies of objects that will outlive us by unimaginable margins. It's like being given access to a play that hasn't been written yet, being allowed to read the script for Act 5 while Act 1 is still in progress, knowing how it ends while the characters are still making their entrances. The ancient Greeks also understood the difference between chronos and kairos, between chronological time and meaningful time. Chronos is clock time, calendar time, the steady tick of seconds and minutes and hours. Kairos is the right moment, the opportune time, the instant when something significant happens. A lifetime can pass in Chronos without anything particularly important occurring, while a few moments of Kairos can change everything. The approach, these first 2 billion years of slowly closing distance, is pure Chronos. Clock time stretched to cosmological scales. Nothing significant will happen during most of it. No dramatic moments, no sudden changes, no obvious milestones. Just the steady, patient convergence of two galaxies following gravitational laws, getting infinitesimally closer with each passing year, building toward a kairos moment that's still billions of years away. And yet, knowing it's coming transforms the chronos into something more meaningful. Every year of approach is a year closer to first contact. Every million years of slow convergence is another step along a path that leads inevitably to transformation. The slowness doesn't diminish the drama, it enhances it, building tension across time scales that make human history look like an eye blink. Right now, tonight, as you drift towards sleep, the approach continues. The Milky Way and Andromeda fall toward each other at 110 kilometers per second, covering distances that seem vast by human standards, but are barely noticeable in cosmic terms. The dark matter halos interpenetrate more deeply. The gravitational binding between both galaxies grows infinitesimally stronger. The satellites orbit unaware of their eventual fate, and somewhere in both galaxies, stars form and die, planets orbit their suns, and the ordinary business of cosmic existence continues, completely indifferent to the collision that will transform everything billions of years from now. The approach is patient, inexorable, beautiful in its slowness and terrible in its certainty. 2 billion years of gradual convergence building toward a moment of first contact that will change everything, that will begin the violent transformation of both galaxies into something new. But we're getting ahead of ourselves again. The approach is still in its early stages, the collision still billions of years away. For now, let's just appreciate the slow dance, the gradual spiral, the patient fall of two titans toward each other through the darkness, following trajectories determined billions of years ago, approaching their destiny with the perfect inevitability of mathematics and the sublime patience of cosmic time. 4 billion years from now, give or take a few 100 million years depending on whose simulation you trust, something remarkable will happen. The Milky Way and Andromeda, after billions of years of patient approach, will finally touch. Not touch in the way solid objects touch. There will be no impact, no crash, no moment of collision that you could point to and say, there, that's when it happened. Galaxies are mostly empty space, and their first contact will be more like two clouds interpenetrating than two cars colliding. But it will be contact nonetheless. The moment when the outer regions of both galaxies begin to feel each other's presence, not as distant gravitational influence, but as immediate tidal disruption. Astronomers call this first close passage the pericentric passage, the point of closest approach, the moment when the distance between both galaxies reaches its minimum before they swing apart again. And while first contact might sound gentle, almost romantic, the reality will be anything but. This is when the violence really begins, when tidal forces become strong enough to tear at both galaxies' structures, when the slow gravitational dance suddenly becomes a spectacular display of cosmic destruction and creation happening simultaneously. Let's imagine you could somehow watch this from a safe vantage point, perhaps from a planet orbiting a star in one of the galaxies, assuming any planets have survived the Sun's red giant phase and the various other catastrophes that will befall the solar system between now and then. More likely, we're imagining an impossible observer, someone with the patience to watch events unfold over millions of years and the vision to see the full electromagnetic spectrum. But imagination is what we have, so let's use it. The approach during those final few 100 million years before first contact will have already transformed the night sky beyond recognition, Andromeda will no longer be that faint smudge requiring dark skies and keen eyes to spot. It will dominate the northern sky, sprawling across perhaps 60 or 80 degrees of arc. That's roughly the width of your hand held at arm's length. Multiplied by 6 or 8, its spiral structure will be visible to the naked eye, individual star-forming regions glowing in different colours, the dark dust lanes threading through the spiral arms, creating patterns of light and shadow across the sky. But it won't look quite right. The spiral structure will be distorted, warped by tidal forces that are already pulling at the outer edges of Andromeda's disk. The arms won't be clean logarithmic curves anymore. They'll be stretched and twisted, bent toward us by our galaxy's gravitational pull. And if you could see the Milky Way's structure from outside, which you can't because we're embedded in it, you'd notice the same distortions in our spiral arms, the same warping and stretching as Andromeda's gravity pulls at our outer regions. The satellite galaxies will be in chaos by this point. Some will have already been destroyed, torn apart by tidal forces and scattered into streams of stars. Others will be in wildly unstable orbits, swinging between both galaxies, their trajectories unpredictable as they respond to the complex gravitational field created by two massive objects in close proximity. M32 and M110, Andromeda's companions, might be visible as separate objects or might already be merging with Andromeda's disk, pulled inward by tidal friction. The Magellanic Clouds, if they've survived this long, will be following their own chaotic paths, possibly close to escaping the system entirely or possibly falling toward one galaxy or the other. And then, over the course of perhaps 10 or 20 million years, which is fast in cosmic terms but still agonizingly slow by any human measure, the first contact will happen. The outer edges of both disks will begin to interpenetrate. Stars and gas clouds from the Milky Way will pass through regions of space that contain stars and gas from Andromeda. The dark matter halos, already deeply interpenetrated, will blend even more thoroughly. And the gravitational forces, which have been building for billions of years, will finally become strong enough to trigger the first spectacular consequence of galactic collision: starburst. This is where galaxies colliding becomes creation rather than destruction. You might think that two galaxies crashing together would destroy stars, scatter solar systems, obliterate planets. And while some of that will happen, some stars will be ejected from both galaxies entirely, flung into intergalactic space by gravitational slingshots. Most of the violence will be constructive rather than destructive. The key is the gas. Both galaxies contain enormous quantities of cold molecular hydrogen gas floating in clouds between the stars. In normal circumstances, these clouds are stable, supported by internal pressure against their own gravity. Star formation happens when something disturbs that balance, when a supernova shockwave passes through, or when clouds collide with each other, or when spiral density waves compress the gas. The disturbance triggers gravitational collapse, and new stars ignite. When two galaxies collide, the gas clouds from both galaxies collide too, not in the sense that individual molecules smash into each other. The gas is far too diffuse for that, but in the sense that two clouds of gas moving in different directions meet and have to occupy the same region of space. The result is compression. Shock waves propagate through both clouds, squeezing the gas, increasing its density, triggering gravitational collapse across vast regions simultaneously. The result is what astronomers call a starburst, a period of intense star formation far exceeding the normal rate triggered by the collision. Regions that might have taken hundreds of millions of years to form stars at a normal, leisurely pace suddenly ignite with stellar birth, producing millions or billions of new stars over just a few million years. These starburst regions glow brilliantly in ultraviolet and visible light as massive young stars pour energy into their surroundings, and they shine in infrared as the dust surrounding star-forming regions absorbs that energy and re-radiates it. From that imaginary vantage point on a surviving planet, the starburst regions would be visible as glowing pink and blue patches scattered across both galaxies' disks, where the gas clouds from each galaxy collided, pink from hydrogen gas ionized by the ultraviolet light of hot young stars, blue from the direct light of those massive stars themselves. These regions would appear and fade over millions of years, appearing as gas clouds collide, shining brilliantly as stars ignite and live their short, violent lives, then fading as the massive stars die in supernovae and the starburst peters out. The night sky would be on fire, in a sense, though it would be cold fire, light without heat at these distances, beauty without danger for any observer far enough away from the actual star-forming regions. It would be a slow-motion fireworks display stretching across dozens of degrees of sky, lasting for millions of years, creating light shows that would make the northern lights seem like candle flickers by comparison. And threading through all of that, becoming visible as the first contact progresses, would be the tidal tails, those long, thin streams of stars pulled out of both galaxies by tidal forces, arcing across the sky like cosmic brush strokes. When galaxies collide, their disks don't stay neat and contained. The differential gravitational pull, stronger on the side facing the other galaxy, weaker on the far side, creates tidal bulges that get pulled out into long streams of material. These streams can stretch for hundreds of thousands of light years, curving gracefully through space, visible as faint glows of starlight, tracing the gravitational chaos of the collision. We've seen these tidal tails in other colliding galaxies. The antennae galaxies have spectacular tails stretching far beyond their disrupted disks. The mice galaxies each have a long tail of stars streaming behind them like cosmic hair. The tadpole galaxy's tail is so prominent it gives the galaxy its name. These aren't rare or unusual features, they're the standard signature of galactic collisions, the inevitable consequence of tidal forces acting on extended structures in close gravitational encounters. The Milky Way and Andromeda will develop their own tidal tails during first contact, probably multiple tails as different parts of each galaxy respond to tidal forces in different ways. These tails will arch across the sky, visible as faint rivers of starlight, slowly changing shape over millions of years as more stars are pulled out and added to the streams. Some of those stars will eventually fall back into one galaxy or the other. Others will be scattered into intergalactic space, orphaned from both galaxies, destined to drift alone through the void for billions of years. There's something both terrifying and beautiful about watching structures tear themselves apart, isn't there? Humans have always been drawn to spectacles of destruction, from fireworks to demolitions to storm watching. We stand at safe distances and watch things fall apart, finding beauty in the chaos, meaning in the transformation. Perhaps it's because destruction reveals hidden structures, shows us what things are made of, proves that even seemingly permanent objects are temporary when subjected to sufficient force. The Hindu god Shiva is often called the Destroyer, which makes him sound like a villain in the Western mythological framework, where creation is good and destruction is bad. But Shiva is more complex than that. He's the destroyer and the creator, the same deity responsible for both endings and beginnings, because in Hindu cosmology, these aren't opposite forces. They're the same force viewed from different moments in the cycle. You can't have creation without destruction. The old must be cleared away to make space for the new. Death and birth are two sides of the same cosmic process. The collision between the Milky Way and Andromeda embodies that principle perfectly. Yes, the beautiful spiral structures of both galaxies are being destroyed during first contact. Yes, the organized rotation is being disrupted. Yes, tidal forces are tearing both structures apart. But that destruction is simultaneously creating new stars at rates far exceeding what either galaxy could produce alone, creating spectacular structures like tidal tails and starburst regions, creating the conditions that will eventually allow both galaxies to merge into something larger and more massive than either was separately. Medieval alchemists talked about the nigredo, the blackening, the first stage of transformation, where matter is broken down into its base components before it can be reformed into something higher. You had to destroy the original substance, reduce it to prima materia, before the work of transformation could begin. The collision is the nigredo of both galaxies, the breaking down that precedes the building up, the destruction that enables creation. The sublime, that particular aesthetic category that combines terror and awe, beauty and fear, attraction and repulsion, seems perfectly suited to describing galactic collisions. The philosopher Edmund Burke, writing in the 18th century, argued that the sublime comes from contemplating things that are vast, powerful and dangerous, but which we experience from a position of safety. A violent storm viewed from a secure shelter. A towering mountain that could kill you if you fell, but which you observe from stable ground. The collision between two galaxies viewed from 4 billion years' distance. We're safe from this collision. We won't be here to experience it. Our species will be long extinct. Our sun will be dead or dying. Earth will be uninhabitable or consumed. We observe the coming destruction from perfect safety, separated by an unbridgeable gulf of time, able to appreciate the spectacle without suffering the consequences. That's what makes it sublime rather than merely terrifying. The combination of vast power and personal safety, cosmic violence and temporal distance. But the first contact isn't the end of the story. It's barely the beginning, because after the two galaxies swing close together, after the tidal forces tear at both structures, and the starburst regions ignite, and the tidal tails stream across the sky, something interesting will happen. They'll separate again. Not completely, not permanently, but enough that there will be a breathing space, a moment of relative calm before the second passage. Remember that angular momentum we talked about earlier, that sideways motion that makes this a spiral approach rather than a head-on collision. That angular momentum doesn't disappear when the galaxies reach their first close passage. It carries both galaxies past each other and back out to some separation distance before gravity drags them back together for another pass. It's like two dancers spinning around each other, coming close, spinning apart, coming close again, each pass bringing them slightly closer to the final embrace. How many passes will there be? The simulations vary. Some show 2 major close passages, others show 3 or even 4 before the final merger. It depends on the exact initial conditions, the precise velocities, the masses, the angular momentum, the distribution of dark matter. Small changes in any of these parameters can significantly affect the number and timing of close passages, but all the simulations agree on the general pattern. Multiple close approaches, each one more violent than the last, each one stripping more stars and gas from both galaxies, each one bringing them closer to the inevitable merger. The first contact is special, though, because it's the moment when the collision transitions from theoretical to actual, from distant future to immediate present. Before first contact, the collision is something approaching, something you can still imagine might somehow be avoided, even though the mathematics says otherwise. After first contact, there's no more pretending. The destruction has begun. The transformation is underway. The countdown to Milkomeda has entered its final phase. Ancient cultures often mark transformative moments with fire. Funeral pyres to release spirits from bodies, sacred flames to purify offerings, the burning of old year's effigies to make way for the new. Fire was transformation made visible, destruction that cleared the way for renewal, the element that separated before from after. The starburst regions igniting during first contact are cosmic fire, marking the transformation of both galaxies from separate entities into participants in a merger that will eventually consume both identities. The sky catches fire, in that sense, not with heat but with light, not with chaos but with creation, not with an ending but with a beginning that looks like an ending, that feels like destruction, but is actually the first stage of building something new. The fire burns cold and patient, lasting millions of years, creating billions of stars, transforming both galaxies irreversibly. And somewhere in all that chaos, assuming they still exist, assuming they've survived the sun's death and the various catastrophes that will reshape the solar system between now and then, any observers watching from the region that once was Earth's cosmic neighbourhood will witness the most spectacular display ever visible in the night sky. Two galaxies tearing each other apart and simultaneously creating something magnificent from the wreckage. First contact, the moment everything changes. The touch that transforms, the fire that creates by destroying, the beginning of the end, or the end of the beginning, depending on your perspective. And it's still just the opening act. There's so much more violence to come, so much more beauty to witness, so many more passes before the final merger. But this first touch, this moment when the sky catches fire and the spiral structures begin their transformation into chaos, this is when the collision becomes real, becomes visible, becomes undeniable. The approach is over, the collision has begun, and there's no going back. After first contact, after the sky catches fire and the tidal forces tear at both galaxies and the starburst regions ignite across both disks, you might think the story is over. Two galaxies touch, merge, done. But the universe doesn't work that efficiently. The merger isn't an event, it's a process. A long, drawn-out process that unfolds over multiple encounters, each one more violent than the last, each one bringing both galaxies closer to the inevitable moment when they can no longer separate. This is where the dance metaphor becomes more than just poetic language. It's actually the best way to describe what happens. After that first close passage, the Milky Way and Andromeda swing apart again, carried by the angular momentum they've retained, pulled back out to some separation distance before gravity drags them back together. They approach a second time, swing close, tear at each other's structures, then separate again, and then a third time, possibly a fourth, depending on the exact dynamics. Each pass brings them closer. Each separation is shorter than the last, until finally, after several billion years of this gravitational choreography, they merge completely and the dance ends. Astronomers call this orbital decay, the gradual shrinking of orbits over time as energy gets dissipated. It's the same process that makes satellites eventually fall back to Earth, the same mechanism that will eventually cause the moon to either crash into Earth or be flung away into space over timescales measured in tens of billions of years. orbits aren't perfectly stable. They leak energy in various ways, and as energy dissipates, the orbit shrinks, bringing the orbiting objects closer together. For galaxies, the energy dissipation happens primarily through tidal friction. Every time the galaxies swing close to each other, tidal forces raise bulges in both structures, regions where material is pulled toward the other galaxy. These bulges contain mass, and that mass creates gravitational drag that pulls on both galaxies, slowing down their orbital motion slightly. With each pass, both galaxies lose a bit of their orbital energy. With each separation, they don't swing quite as far apart as before. With each approach, they come a bit closer than last time. It's slow. Even by cosmic standards, it's slow. The time between first and second passage might be 500 million years. Between second and third, maybe another few hundred million. The orbital period gradually shortens as the orbit decays, but we're still talking about timescales that dwarf the entire history of complex life on Earth. Dinosaurs could evolve, reign supreme, and go extinct multiple times in the gap between one passage and the next. But slow doesn't mean gentle. With each close passage, the violence intensifies. The first encounter produces tidal tails and starburst regions, disrupts the outer spiral arms, starts pulling stars out of both galaxies. The second encounter tears deeper into both structures, disrupts the spiral arms more severely, pulls out longer tidal streams, triggers even more intense star formation. By the third or fourth pass, both galaxies are no longer recognizable as clean spiral structures. They're distorted, stretched, wrapped around each other like two dancers who've gotten tangled up in each other's arms. Computer simulations of galaxy mergers have been run thousands of times with different parameters and assumptions, and they all show this same basic pattern. The exact number of close passages varies. Some simulations show 2 major encounters before final merger. Others show 3 or 4. The timing varies depending on the masses, the initial velocities, the angular momentum, the distribution of dark matter. But the general sequence is always the same. Approach, close passage, separation, approach again, closer passage, shorter separation, and so on, until the galaxies can no longer pull apart and the merger becomes inevitable. One of the fascinating things about these simulations is how differently dark matter and regular matter behave during the merger. Remember that dark matter makes up about 85% of each galaxy's mass, but it doesn't interact with light or with itself except through gravity. When the dark matter halos of both galaxies interpenetrate during a close passage, the dark matter particles just pass through each other. They don't collide, don't bounce off each other, don't create shock waves or friction. They just flow through like 2 clouds of mist merging, their trajectories affected only by the combined gravitational field they create together. This means the dark matter halos merge first, long before the visible parts of the galaxies complete their merger. With each passage, the dark matter from both galaxies mixes more thoroughly. The distinction between Milky Way dark matter and Andromeda dark matter becomes more meaningless, until eventually you just have one combined dark matter halo surrounding the merging visible structures. The dark matter merger is smooth, gradual, almost peaceful compared to what's happening with the gas and stars. The gas behaves completely differently. Gas clouds do collide when galaxies meet. 2 clouds of molecular hydrogen moving in different directions can't occupy the same space without interacting. When they meet, they crash into each other, not like solid objects hitting, but like 2 streams of water colliding, creating turbulence and shock waves. The collision compresses the gas, heats it, strips electrons from atoms, creates all those spectacular starburst regions we talked about earlier. The gas collision is violent, energetic, creative. It's where most of the visible fireworks happen. And then there are the stars themselves, which behave in a third way entirely. Individual stars almost never collide with other stars, even during galactic mergers, because space is so astonishingly empty. The distances between stars are enormous compared to the stars themselves. If you shrank the Sun down to the size of a grain of sand, the nearest star would be about 4 kilometers away. If you populated an entire galaxy with sand-grained suns at that scale, you'd have vast stretches of empty space between them. This means that when the Milky Way and Andromeda collide, when billions of stars from each galaxy pass through the region occupied by the other galaxy, almost none of them will actually hit each other. They'll pass through like 2 swarms of bees flying through each other, each bee missing all the other bees by enormous margins. The stars will have their orbits disrupted by the combined gravitational field. They'll be flung onto new trajectories, some ejected from the system entirely, others captured into new orbits around the merged galaxy's center. But actual star-on-star collisions will be rare, perhaps a few hundred events across both galaxies during the entire merger. Statistically negligible when you're dealing with hundreds of billions of stars. Our own Sun, if it still existed during the merger, would almost certainly pass through the entire collision without coming close to another star. The odds of a collision are so remote that they're not worth worrying about, even over the full timeline of the merger. What the Sun would experience is a changing gravitational field as it responds to the combined pull of both galaxies, and it might end up on a very different orbit around Milkomeda's center than it currently follows around the Milky Way's center. But a collision? Almost impossible. This is important because it means the destruction we're talking about is structural rather than physical. We're not destroying stars or solar systems. We're destroying the organization, the pattern, the beautiful spiral structure that gives galaxies their form. It's the death of order rather than the death of objects, the end of the spiral arms, the disruption of organized rotation, the scattering of stars that were once part of coherent structures into chaotic orbits. Form dies while substance persists. Medieval artists created images called the Danse Macabre, the dance of death, showing skeletons leading people from all walks of life in a macabre dance. Kings and peasants, bishops and merchants, young and old, all dancing with death, all equal in their mortality, all destined for the same ending regardless of their earthly status. The dance was meant as a memento mori, a reminder that death comes for everyone, that all earthly distinctions are temporary, that the final dance equalizes all dancers. The collision between the Milky Way and Andromeda has that same quality of inevitable equality. Both galaxies are comparable in mass, neither significantly more powerful than the other. They're equals in their mortality, both destined for the same transformation, both participating in a dance that will destroy their individual identities, even as it creates something new from their combined mass. There's no victor in this dance, no survivor, no galaxy that escapes transformation. Just 2 dancers spiraling together toward a merger that will consume both. But where the medieval dance of death was meant to inspire dread, the galactic dance inspires something more complex, a mixture of awe and melancholy, beauty and loss, acceptance and wonder. Perhaps because we're watching from such enormous distance, both spatial and temporal. Perhaps because the scale is so vast it becomes abstract, more mathematical than visceral. Or perhaps because we've learned to see beauty in transformation, to appreciate endings as part of cycles rather than as final terminations. Hindu cosmology describes Shiva performing the Tandava, the cosmic dance that destroys the universe at the end of each cycle, clearing the way for Brahma to create it anew. The dance is violent, reality-shattering, but it's also necessary. The old universe must be destroyed before the new universe can be born. Creation and destruction aren't opposites in this framework. They're partners in an eternal cycle, each one necessary for the other, each one incomplete without the other. The multiple passes of the Milky Way and Andromeda are their own version of cosmic dance, less ritualized than Shiva's Tandava, but following the same basic pattern. Each encounter destroys a bit more of the original structures. Each separation allows both galaxies to briefly maintain their identities as separate entities. Each approach brings them closer to the final merger. It's a dance that lasts billions of years, performed to the silent music of gravitational forces, choreographed by the mathematics of orbital mechanics, building toward a finale that's been determined since the first notes played. There's something deeply intimate about repeated encounters, isn't there? Two entities meeting once could be chance, coincidence, and accident of trajectories, but multiple meetings, each one closer than the last, each one more entangled, each one harder to walk away from, that's not chance anymore. That's destiny working itself out, inevitability expressing itself through repeated contact, a relationship deepening with each passage, even though the relationship is one of mutual destruction. Spirals appear everywhere in nature and human culture. The spiral arms of galaxies themselves, obviously, but also the spiral of a nautilus shell growing outward in a perfect logarithmic curve, the spiral of water draining, spinning inward toward the center, the spiral path of a labyrinth, winding toward a center and then back out again, the spiral in Maori Koru designs, representing new life unfurling, the spiral in Buddhist mandalas, representing the journey toward enlightenment, the spiral in Celtic art, suggesting interconnection and cycles. The orbital decay of two galaxies follows its own spiral pattern, approaching the center, swinging around, moving back out, approaching again closer than before, spiraling gradually inward toward the inevitable merger at the center. It's a spiral in four-dimensional space-time rather than on a flat surface, but the pattern is the same. Gradual convergence, progressive tightening, each loop bringing you closer to the center until you reach the point from which there's no return. How many loops will there be? The simulations suggest somewhere between 2 and 4 major close passages, depending on the exact parameters. 2 seems like too few, barely enough to establish the pattern before it ends. 4 seems almost excessive. Surely by the 4th pass, both galaxies would be too disrupted to separate again. 3 feels right, in that way that odd numbers often feel more balanced and complete than even numbers. A beginning, a middle, and an end. Thesis, antithesis, synthesis, past, present, future. But the universe doesn't care about our aesthetic preferences. The number of passes will be whatever the mathematics determines, whatever follows naturally from the masses and velocities and angular momentum of the system. It might be 2 clean passes or 4 messy ones or some intermediate number, where it's hard to say exactly where one pass ends and the next begins, because the galaxies never quite separate completely. The simulations give us ranges and probabilities rather than certainties, because small uncertainties in the initial conditions lead to significant variations in the outcome. What we can say with confidence is that the total process, from first contact to final merger, will take somewhere between 5 and 6 billion years. That's the timeline that appears consistently across most simulations. 4 billion years from now for first contact, another 5 or 6 billion for the dance to play out, for the multiple passes to occur, for the orbital decay to bring both galaxies close enough that they can no longer separate. 10 or 11 billion years from now, Milkomeda emerges from the wreckage. Earth won't exist to witness any of this. The sun will have swollen into a red giant about 5 billion years from now, probably consuming Mercury and Venus, and rendering Earth uninhabitable long before that. By the time first contact happens, the sun will be a white dwarf, a stellar corpse cooling slowly in the darkness, all its nuclear fuel exhausted, no longer capable of supporting life on any planet. By the time the merger completes, the sun will have been dead for longer than it was alive. But the galaxy will persist. The stars that make up the Milky Way, or at least those that don't get ejected during the collision, will continue orbiting around Milkomeda's centre for billions of years after the merger. New stars will form from gas clouds compressed during the collision. Planets will orbit those new stars. Possibly life will emerge on some of those planets. The universe will continue, indifferent to the transformation, ready to begin new stories in new forms. There's a certain privilege in knowing how this story ends while living so far from its conclusion. We're separated from the dance by billions of years, safe from any consequences, able to appreciate it as spectacle and mathematics without experiencing it as catastrophe. We can trace the spiral path from beginning to end, watch the simulation play out, understand the forces that drive the dance, all while knowing that we'll never see it happen, that it exists for us only as intellectual exercise and cosmic poetry. The dancers circle each other in the darkness, following paths determined billions of years ago, moving through their choreographed destruction with the patience of geological time and the inevitability of mathematics. Each pass brings them closer. Each separation grows shorter. The dance speeds up as it approaches its conclusion, orbital periods shrinking as energy dissipates, until finally there's no more distance to close, no more separation possible, no more dancing as separate entities, but only the merged form of Milkomeda settling into its new equilibrium. But we're not there yet. The dance continues. The spiral tightens. The passes become more violent and more intimate with each encounter. And through it all, the dark matter flows, and the gas collides, and the stars pass through each other like ghosts, creating beauty from destruction, finding grace in gravitational physics, performing a dance that will last longer than most species exist, but which follows laws as simple and elegant as any waltz. The dance of destruction continues, patient, inevitable, beautiful in its violence and violent in its beauty, and with each pass, both galaxies become a little less themselves, and a little more what they will become together. At the centre of every large galaxy, hidden within the crowded chaos of the galactic bulge, where millions of stars orbit in a relatively small space, sits something dark. Not dark in the metaphorical sense, though that works too, but genuinely, physically dark. A region of space-time so warped by concentrated mass that nothing can escape from it, not even light. A supermassive black hole, the gravitational anchor around which the entire galaxy ultimately spins, the dense heart of darkness that helped the galaxy form in the first place, and has been growing steadily ever since by consuming anything that ventures too close. Our Milky Way has one, Sagittarius, a star as we call it, weighing in at about 4 million times the mass of the Sun. That's enormous by human standards. If you could somehow replace the Sun with Sagittarius, a star, its event horizon would extend almost to Mercury's orbit. But by the standards of supermassive black holes, it's actually rather modest, almost quaint, really, like a compact sedan compared to the 18-wheelers sitting at the centres of more massive galaxies. Andromeda has one too, of course, M31 star, located at the center of Andromeda's bulge, weighs somewhere between 100 and 200 million solar masses, depending on which measurements you trust. That's 30 to 50 times more massive than our black hole. If our black hole is a compact sedan, Andromeda's is an articulated bus, something you definitely want to give a wide berth when it's moving through traffic. When the Milky Way and Andromeda merge, these two black holes will eventually merge as well. It's not optional, not something that might happen if conditions are right. It's inevitable, written into the physics just as surely as the galactic merger itself. Two massive objects in a gravitational system will always try to find each other, always spiral inward toward the deepest part of the gravitational well, always seek the configuration with the lowest possible energy. And the lowest energy configuration for two black holes in a merged galaxy is one black hole at the center rather than two. But getting them to actually merge turns out to be surprisingly difficult. Not impossible. We know it happens because we've detected the gravitational waves from smaller black hole mergers, and we see single massive black holes at the centers of galaxies that clearly formed from multiple mergers. But the path from two black holes in the same galaxy to one merged black hole involves some interesting physics, and at least one problem that took decades to fully understand. Let's start with what happens during the galactic merger. In the early stages, when the galaxies are still doing their multiple pass dance, both black holes are still separated by hundreds of thousands or millions of light years. They're aware of each other gravitationally. Everything with mass is aware of everything else with mass in the universe, but they're too far apart for that awareness to matter much. They're each still the gravitational center of their own galaxy, each still doing their own thing, unbothered by their eventual partner. But as the merger progresses, as both galaxies become more thoroughly mixed and their stars scatter into new orbits, both black holes start spiraling toward the center of the combined system. This happens through a process called dynamical friction, which is a wonderfully misleading name because it doesn't involve friction in any normal sense. There's no rubbing, no heat generation, no surfaces in contact. It's pure gravity, creating an effect that looks like friction. Here's how it works. When a massive object moves through a sea of less massive objects, like a black hole moving through a region full of stars, it gravitationally attracts the stars as it passes them. Stars behind the black hole get pulled forward slightly, speeding them up. Stars in front get pulled backward, slowing them down. This creates a wake of stars trailing behind the black hole, a region where the stellar density is slightly higher than average. That wake has mass, and that mass gravitationally pulls backward on the black hole, slowing it down. The black hole loses momentum to the wake, which causes it to fall inward toward the center of the gravitational potential. It's similar to how a ship moving through water creates a wake that produces drag on the ship, except instead of water molecules you have stars, and instead of hydrodynamic forces you have gravity. The net effect is the same. The massive object slows down and sinks toward the center. Over millions of years, dynamical friction causes both black holes to spiral inward through the merged galaxy, losing energy to the stars around them, falling toward the center of mass of the combined system. Eventually, they get close enough that they form a bound binary, two black holes orbiting each other, locked in gravitational embrace, no longer separate entities wandering through the galaxy, but a single system with a shared future. And this is where things get interesting. And by interesting, I mean problematic for several decades, until theorists figured out the solution. Once the two black holes form a binary, they continue to lose energy and spiral inward toward each other. At first, this happens through dynamical friction with surrounding stars. Stars passing close to the binary system interact gravitationally and carry away energy, causing the binary to shrink. But eventually, the binary gets tight enough that there aren't many stars on orbits that pass close enough to interact effectively. The binary reaches a separation of about 1 parsec, roughly 3 light years. And then what? This was called the final parsec problem. How do the black holes get from 1 parsec separation down to the final merger? Dynamical friction becomes ineffective at that point because the binary has already ejected or scattered most of the stars that could have interacted with it. The black holes are stuck, circling each other at 1 parsec separation, unable to get closer through the mechanisms that brought them together initially. The problem haunted theorists for years because we knew black hole mergers had to be happening. The evidence was there in gravitational wave detections and in the single massive black holes at galaxy centers, but the path to merger seemed to be blocked. The solution, it turns out, involves multiple mechanisms working together. Gas flowing through the galactic center can carry away energy from the binary. Continued interactions with stars on specific types of orbits can slowly drain energy even after most stars have been scattered. And most importantly, once the black holes get close enough, within a few hundredths of a parsec, gravitational wave emission becomes significant. Gravitational waves are ripples in space-time itself, produced whenever massive objects accelerate. 2 black holes orbiting each other create gravitational waves that carry energy away from the system. At large separations, the energy loss is negligible, but as the black holes get closer and orbit faster, gravitational wave emission increases dramatically. Eventually, it becomes the dominant mechanism for energy loss, and the binary spirals inward on an inexorable path toward merger. The final stages happen quickly, at least compared to the millions or billions of years it took to get there. Once gravitational wave emission takes over, the inspiral accelerates. The black holes orbit faster and faster as they spiral closer together, producing stronger and stronger gravitational waves, losing energy more and more rapidly, creating a runaway process that ends only when both event horizons merge into one. The merger itself is difficult to visualize because it involves the violent warping of space-time in ways our everyday intuition can't really grasp. 2 regions of infinitely curved space-time approach each other, their event horizons stretching and distorting, reaching toward each other like liquid drops about to touch. And then, in a fraction of a second, they merge. The event horizons connect, flowing together like 2 soap bubbles becoming one. The space-time curvature settles into a new equilibrium. Where there were 2 black holes, now there is one. The energy released in that merger is staggering. A typical supermassive black hole merger can convert several % of the total mass into pure energy, radiated away as gravitational waves. For the merger of Sagittarius A star and M31 star, with a combined mass around 200 million solar masses, that means several million solar masses worth of energy released in gravitational waves over the final hours or days of inspiral and merger. That's more energy than all the stars in both galaxies will produce over their entire lifetimes, released in a burst lasting hours, not released as light or heat or particles, released as ripples in the fabric of space-time itself, as gravitational radiation propagating outward at the speed of light, stretching and squeezing space itself in a pattern that carries information about the black holes that created it. We won't see these gravitational waves directly. They'll have travelled billions of light years by the time they reach the region where Earth once was, and they'll have been redshifted by the expansion of space, weakened by distance diluted across space-time, but future instruments might detect them. LISA, the Laser Interferometer Space Antenna, a proposed space-based gravitational wave detector, is designed to detect exactly this kind of event. Supermassive black hole mergers, the collisions of giants, the moments when dark hearts merge. If LISA or something like it exists when the merger happens, and if it's sensitive enough, it might detect the gravitational waves from our own galactic collision rippling outward through space-time, carrying news of the merger to any observers lucky enough to be watching with the right instruments. The waves would tell them about the masses of both black holes, the speed of their final inspiral, the properties of the merged black hole that emerged, all of that information encoded in the pattern of stretching and squeezing as the waves pass by. What happens to stars near the black holes during this process? Nothing good, typically. When you have two supermassive black holes spiraling toward each other at the center of a merged galaxy, any star that wanders too close is likely to have a bad time. The gravitational field in that region becomes chaotic, complex, difficult to navigate. Some stars will be ejected entirely, flung out of the galaxy at high speeds by gravitational slingshots. Close encounters with one or both black holes that transfer energy and send the star flying. These are called hypervelocity stars, and we've detected several in our own galaxy that were likely ejected from the galactic center by interactions with Sagittarius A star, or with the binary black hole system that may have existed there in the past. Other stars will simply fall into one of the black holes, crossing the event horizon and disappearing forever, their mass added to the black hole's growing horde. From our perspective outside, we'd see the star approach the event horizon, its light becoming increasingly redshifted as it falls deeper into the gravitational well, appearing to slow down as it approaches the horizon, asymptotically freezing at the edge from our perspective, even though from the star's perspective it crosses the horizon in finite time and is crushed to singularity shortly thereafter. The region around merging supermassive black holes is one of the most violent environments in the universe, a place where space-time is tortured into extreme curvature, where tidal forces can tear stars apart, where the normal rules of physics are stretched to their limits. And yet, paradoxically, it's also a place of profound darkness. Black holes produce no light. Their mergers produce no visible flash, no spectacular display that you could photograph with a telescope. All the violence happens in darkness, hidden behind event horizons, invisible to anything but gravitational wave detectors. There's something fitting about that, isn't there? The final act of the galactic merger, the moment when the dark hearts at each galaxy's center finally unite, happens in darkness. The most energetic event in the entire collision, the merger that releases more energy than all the stars in both galaxies, is also the most hidden, the most private, the most removed from observation by anything that relies on light. Buddhist philosophy has a concept called shunyata, often translated as emptiness or voidness. It doesn't mean nothingness in the nihilistic sense. It means the absence of inherent existence, the recognition that all things are interdependent and lack permanent, independent essence. Everything is empty of self-nature, existing only in relation to everything else, arising and passing away in patterns of cause and effect, with no solid, unchanging core. Black holes are the universe's physical embodiment of shunyata, in a way. They're defined by absence, the absence of light, the absence of any signal from within the event horizon, the absence of any way to know what's inside except through external gravitational effects. They exist only as relationships to the space around them, only as curvature in space-time, only as gravitational influence on things that haven't fallen in yet. The interior is cut off from the universe, causally disconnected, unknowable. What exists is the absence, the void, the empty place where space-time curves back on itself. Medieval cosmologies place the firmament, the sphere of fixed stars, at the outer edge of the cosmos, and beyond that, nothing. Not empty space, but actual nothing, the absence of existence itself, the void that existed before creation. Black holes are like holes poked through the fabric of space-time, windows into that primordial nothing, places where the universe folds back on itself and disappears into absence. Dragons in mythology often guard treasure, sitting on hoards of gold in deep caves, threatening anyone who approaches. The black holes at galactic centers are cosmic dragons, sitting on hoards of mass accumulated over billions of years, threatening any star that approaches too closely with obliteration. And when two dragons meet, when two black holes merge, it's not a fight. It's more like two shadows flowing together into one darker shadow, two absences becoming one larger absence, two voids merging into unified darkness. The result of the merger will be a single supermassive black hole weighing around 200 million solar masses, assuming both black holes contribute roughly what we expect, and nothing dramatic happens during the merger to eject mass from the system. This merged black hole will sit at the center of Milkomeda, the gravitational anchor around which the entire merged galaxy will organize itself, the dark heart that holds everything together through its gravitational influence, while remaining forever hidden behind its event horizon. It will be larger than either black hole was individually, but not by as much as you might expect, because some of the mass gets converted to energy and radiated away as gravitational waves. It will probably be spinning rapidly. Black hole mergers typically produce rapidly spinning remnants, their angular momentum conserved and concentrated as the two event horizons merge, and it will settle down relatively quickly, on timescales of hours or days, the violent oscillations of merger fading as the event horizon relaxes into a smooth surface, and space-time around it settles into equilibrium. And then it'll just sit there, growing slowly as occasional stars or gas clouds fall in, spinning gradually slower over billions of years as it radiates away angular momentum. Being a black hole, which is mostly a passive process, once the dramatic moments of formation and merger are complete, waiting patiently for whatever comes next, another merger billions of years from now, if Milkomeda collides with another galaxy, or simple patience as the universe expands and cools, and eventually, trillions of years in the future, even black holes evaporate through Hawking radiation. There's something almost anticlimactic about the black hole merger compared to the spectacular visible fireworks of the galactic collision. The starburst regions and tidal tails and scattered stars are visually impressive, photogenic, the kind of thing that makes compelling images. The black hole merger releases more energy but happens in darkness, visible only to gravitational wave detectors, comprehensible only through mathematical descriptions of space-time curvature. It's the most powerful event in the entire collision, but also the most hidden. Perhaps that's appropriate. The most profound transformations often happen in darkness, in private, hidden from observation. Seeds germinate underground before sprouting. Metamorphosis happens inside cocoons. The deepest personal changes occur in internal spaces that others can't access. The merger of black holes follows the same pattern. The most energetic transformation happens in the most private space, behind event horizons, in regions causally disconnected from external observation. When the merger is complete, when the gravitational waves have propagated away and the space-time curvature has settled, and the new black hole sits at Milkomeda's center, very little will have changed from an external perspective. There will be one black hole where previously there were two, occupying essentially the same place at the galactic center, doing essentially the same job of holding the galaxy together gravitationally. The visible fireworks will still be happening, stars still scattering, gas clouds still colliding, starburst regions still shining. The black hole merger is just one event in a process that spans billions of years, important but not uniquely significant, dramatic but hidden. The dark hearts merge in darkness, the void becomes one, the dragons flow together into unified shadow, and the universe continues, indifferent to the transformation, ready to build new structures around the new black hole, waiting patiently for whatever comes next in the endless cycle of cosmic evolution. Two became one in the darkest way possible in the most hidden place, releasing more energy than imaginable while producing no visible light, performing the most powerful transformation in absolute silence and eternal darkness, becoming something new while remaining fundamentally unchanged in character. Still a black hole, still a void, still a dark heart at a galaxy's center. Just bigger now, and spinning. After billions of years of approach and collision, after multiple violent passes and tidal disruptions, after the black holes merge and the stars scatter, and the gas clouds finish their final bursts of star formation, something new emerges from the wreckage. Not immediately. Galaxies don't snap into new configurations like puzzle pieces clicking into place. But gradually, over hundreds of millions of years, the chaos settles, the orbits relax, the violence fades, and where there were once two spiral galaxies, there is now one elliptical galaxy, massive and smooth and featureless, its spiral structure erased, its organized rotation transformed into random stellar motion. We've already given it a name, this galaxy that won't exist for another 10 billion years. Milkomeda, or sometimes Milkdromeda, if you prefer the syllables blended differently. It's a portmanteau, one of those hybrid words created by mashing two names together, like brunch or smog or Brexit. Take Milky Way, take Andromeda, combine them into something that sounds vaguely official and slightly silly at the same time. Milkomeda. The name is informal, coined by astronomers and science communicators who needed something to call the merged galaxy in their papers and presentations. It's not an official designation. The International Astronomical Union hasn't voted on it, won't vote on it for billions of years when the merger is actually happening and when humans almost certainly won't exist to care what it's called. But the name has stuck because we need something to call it, some way to refer to the future galaxy that will emerge from our current one, and Milkomeda is at least memorable and descriptive, even if it sounds a bit like a pharmaceutical brand name. There's something simultaneously playful and melancholic about naming something that results from the destruction of two things you love, like naming a child after two grandparents who've passed away, honouring the memory while acknowledging the loss, carrying forward pieces of both identities into something new. Milkomeda will contain stars from both galaxies, mass from both dark matter halos, the merged black holes from both galactic centers. It will be both and neither, a new entity that erases both predecessor identities while preserving their substance. But let's talk about what Milkomeda will actually be, what characteristics it will have, what you'd see if you could somehow observe it from outside. First and most obviously, no more spiral structure. The beautiful arms that currently define both the Milky Way and Andromeda, those elegant logarithmic curves threading through both disks, will be completely destroyed. Spiral arms exist because of organized rotation. The galaxy spins like a disk, and density waves propagate through that disk, creating regions where stars and gas bunch up temporarily before moving on. It's a pattern that depends on coherent rotation, on most stars moving in roughly the same direction at similar speeds. The merger destroys that coherence. Stars from the Milky Way moving in one direction meet stars from Andromeda moving in a different direction. Tidal forces scatter stars onto new orbits that have nothing to do with their original paths. The organized rotation gets converted into random motion. Some stars orbit one way, others orbit the opposite way, others move on highly elliptical orbits that take them far from the galactic center and then plunge back through the core. The net result is a galaxy with no overall rotation, no spiral pattern, no disk structure. Just a smooth, roughly spherical collection of stars moving in essentially random directions. This is an elliptical galaxy, the most common type of massive galaxy in the universe. When we look out at distant galaxy clusters with our telescopes, the giant galaxies at the centers are almost always ellipticals, smooth, featureless, football-shaped distributions of stars with no obvious structure beyond a bright center that gradually fades toward the edges. They're not as photogenic as spirals. They don't have dramatic dust lanes or glowing star-forming regions or elegant arms to catch the eye. They're just there, massive, ancient, sedate, the retirement homes of the galaxy world, populated by old stars living out their long, quiet lives. Milkomeda will be one of these, a giant elliptical galaxy, smooth and featureless, its most dramatic days behind it, settling into a long, slow fade over trillions of years as its stars gradually age and die without being replaced by new ones. Because here's the other major consequence of the merger. Star formation will mostly stop. Not immediately. There will be tremendous bursts of star formation during the collision itself as gas clouds crash together and compress. But once the merger completes, once the gas has been either consumed in star formation or shock heated to such high temperatures that it can't collapse to form new stars, the galaxy will enter a period of quiescence. No more star formation, or at least very little, just occasional stars forming from leftover gas that manages to cool and collapse over billions of years. This happens because the merger destroys the conditions necessary for ongoing star formation. In spiral galaxies, gas naturally accumulates in the disk, where it can cool and form molecular clouds that collapse into stars. The organized rotation helps keep the gas in the disk. The spiral arms create density waves that trigger star formation. It's a sustainable system that can keep producing stars for billions of years as long as there's gas available. In elliptical galaxies, there's no disk to accumulate gas, no organized rotation to keep things tidy, no spiral arms to trigger collapse. Gas that might fall into the galaxy gets shock heated to millions of degrees as it collides with the hot atmosphere surrounding the galaxy. It glows in X-rays, visible only to X-ray telescopes, far too hot to collapse and form stars. Any cold gas remaining from the merger gets used up quickly in the final starbursts, and then there's nothing left to make new stars. So Milkomeda will age. Its stars will slowly evolve, the most massive ones dying first, then progressively smaller stars going through their life cycles and fading. The galaxy will gradually redden as the hot blue stars die off and only the cool red stars remain. Over trillions of years, timescales far longer than the current age of the universe, even those red dwarfs will exhaust their fuel. Eventually, in the unimaginably distant future, Milkomeda will be a collection of stellar remnants, white dwarfs, neutron stars, black holes, all that's left after stars finish their lives. A galaxy of ghosts, slowly fading, slowly dissipating, slowly succumbing to entropy. But that's trillions of years away. In the shorter term, the first few billion years after the merger, Milkomeda will actually be quite luminous, containing all the stars from both predecessor galaxies plus billions of new stars formed during the collision. It will be massive, weighing in at somewhere between 3 and 4 trillion solar masses once you account for all the dark matter from both halos. That makes it one of the more massive galaxies in the local group's eventual evolution, a genuine giant by galactic standards. The size is interesting too. You might expect that combining two galaxies would produce something with twice the diameter, but that's not how it works. Elliptical galaxies are puffed up compared to spirals. Their stars orbit in all directions rather than being confined to a thin disk, so the galaxy extends farther in 3 dimensions. Milkomeda will probably be something like 100 to 200,000 light-years across in terms of where most of its stars are located, though like all galaxies, it won't have a sharp edge. The stellar density will just gradually decrease as you move outward until you can't really say whether you're still in the galaxy or in intergalactic space. And then there's the dark matter halo, which will extend several million light-years from the centre, a vast invisible structure containing most of the galaxy's mass. That halo will be the combined halos from both the Milky Way and Andromeda, thoroughly mixed and relaxed into a new equilibrium. The halo will be roughly spherical, following the same kinds of density profiles that all dark matter halos follow, fading gradually into the cosmic background without any clear boundary. We can compare Milkomeda to other elliptical galaxies we observe in the universe to get a sense of what it will look like. M87, that giant elliptical in the Virgo cluster, the one whose supermassive black hole was photographed by the Event Horizon Telescope in 2019, producing that iconic image of the black hole's shadow surrounded by glowing plasma, is probably a good comparison. M87 is somewhat more massive than Milkomeda will be, but they're in the same general class. Giant ellipticals, smooth and featureless, dominated by old stars, no longer forming new stars at significant rates. Or consider M60, another elliptical in Virgo, or NGC 1399 in the Fornax cluster. These are all galaxies that likely formed through mergers, through the collisions of multiple spiral galaxies over billions of years, each merger adding mass and destroying spiral structure until what remains is a smooth elliptical. Milkomeda will join their ranks, one more elliptical galaxy in a universe full of them, distinguished only by having once been us. There's a certain poetry to the fact that the most common type of massive galaxy forms through the destruction of the most beautiful type. Spirals are gorgeous, photogenic, dynamic, full of structure and star formation and visual interest. Ellipticals are less so. They're important, they're massive, they're scientifically fascinating, but they're not pretty in the same way. They're what spirals become when they grow old and comfortable and settled, when they've finished their dramatic youth and entered their sedate middle age. The ancient phoenix in Greek and Egyptian mythology was a bird that lived for hundreds or thousands of years before bursting into flames and being reborn from its own ashes. It's a symbol of resurrection, of renewal, of death and rebirth as a cycle, rather than as linear progression. The phoenix doesn't avoid death, it embraces it, knowing that death is necessary for rebirth, that endings enable beginnings. The transformation of the Milky Way and Andromeda into Milkomeda has some of that phoenix quality, though perhaps with less literal fire and more metaphorical flame. Both galaxies die, their structures are destroyed, their identities are erased, their spiral forms are consumed in the fire of collision and merger. But what emerges isn't nothing. It's something new, something that preserves the mass and stars and substance of both predecessors while taking on a completely different form. Buddhist concept of Anatman, the doctrine of no self, the recognition that there's no permanent, unchanging essence to anything, seem relevant here. What makes the Milky Way the Milky Way? Its spiral structure, its collection of stars, its dark matter halo. When the merger happens, the stars will still exist, just in different orbits. The dark matter will still exist, just in a new configuration. The mass and substance persist, but the form changes so completely that we can't really call it the Milky Way anymore. The identity dissolves while the components continue. The same happens with Andromeda, and what emerges, Milkomeda, isn't a victor or survivor. It's not the Milky Way that conquered Andromeda or vice versa. It's a new entity that contains pieces of both, but is fundamentally neither. A merged identity that's more than either predecessor alone, but also less than both together. There's melancholy in that, certainly. The beautiful spirals are gone, replaced by something more massive but less interesting to look at. The organized rotation is destroyed, replaced by random motion. The ongoing star formation is shut down, replaced by gradual aging. Everything that made both galaxies dynamic and photogenic and alive feeling is erased in favor of something more stable, but also more static. But there's also beauty in it, if you can accept transformation as a valid end in itself. Milkomeda will exist for trillions of years, far longer than either the Milky Way or Andromeda would have lasted as separate entities. It will be more massive, more gravitationally significant, more capable of influencing its cosmic neighborhood. It will contain all the stars from both predecessors, all the mass, all the substance, just rearranged into a new configuration. Nothing is truly lost except the pattern, the organization, the temporary form that both galaxies happened to have before the merger. In a way, elliptical galaxies are more honest than spirals about what galaxies actually are. Spirals have all this beautiful structure, the arms, the disk, the organized rotation, that makes them look designed, purposeful, meaningful. Ellipticals strip away that structure and show you what's really there. Just a collection of stars and dark matter held together by gravity, moving according to physics, forming whatever configuration minimizes energy. No spiral pattern pretending to be significant, no organized rotation suggesting purpose, just mass and gravity and the inevitable consequences of both. There's a Zen quality to that simplicity, a kind of aesthetic minimalism. The Japanese concept of wabi-sabi, finding beauty in imperfection, in impermanence, in simplicity, might apply to elliptical galaxies. They're not perfect spirals with elegant geometry. They're lumpy, irregular, featureless. But that very simplicity has its own beauty, its own truth, its own honest representation of what galaxies are when you strip away the pretty structures and look at the fundamentals. Milkomeda will be that kind of beautiful. Not photogenic beautiful, not the kind of beautiful that makes stunning images for calendars and posters, but beautiful in its honesty, its simplicity, its massive, unpretentious existence as just a bunch of stars held together by gravity, doing what gravity tells them to do, forming the configuration that physics requires. And perhaps that's the real lesson of the merger, that beauty and identity are temporary, that structure and form are transient, that everything transforms into something else eventually, and that accepting transformation doesn't mean giving up on meaning or significance or value. Milkomeda will matter just as much as the Milky Way and Andromeda mattered, just in a different way. It will influence its cosmic neighborhood, host billions of stars and potentially billions of solar systems, exist as a significant gravitational presence in the universe for trillions of years. It just won't be us anymore, won't be either of us, will be something new that emerged from what we were, carrying forward our substance while abandoning our form, persisting in matter while dissolving in pattern, birth through death, creation through destruction, two becoming one while both cease to be. The phoenix reborn, not as its former self, but as something fundamentally different, carrying forward only the ashes, only the substance, only the matter that remains when form dissolves. Milkomeda, the name we gave to our future, the label we attach to the galaxy that will emerge when we cease to exist as we are. A silly-sounding portmanteau that somehow captures both the playfulness and the profundity of cosmic transformation, both the continuation and the ending, both the birth and the death wrapped together in 4 syllables. Welcome to the universe, Milkomeda. You don't exist yet, won't exist for another 10 billion years. But we've already named you, already modelled you in our simulations, already accepted that you're our inevitable future, the form we'll take when transformation completes, the thing we'll become when we're no longer ourselves. We'll be gone by then, of course. Humanity, Earth, the Sun, everything we know. But the stars will continue, the matter will persist, and Milkomeda will settle into its long, quiet existence, aging slowly over trillions of years, a monument to transformation and merger, and the inevitable consequences of gravity operating over cosmic time. Two became one. Both died in the process. Something new was born from their dissolution, and the universe continues, indifferent and patient, ready to build the next structures, start the next transformations, follow the next chapters in its endless story of matter and energy, and the strange, temporary patterns they form before dissolving into something else. We started this journey with a question implied by the framing: which galaxy wins? When 2 titans of roughly equal mass collide, when comparable forces meet in gravitational combat, surely one must emerge victorious, one must dominate, one must survive, one must impose its structure and identity on what remains. That's how conflicts work, isn't it? Winners and losers, victors and vanquished, survival and defeat. Except the universe doesn't work that way. Not at galactic scales, not over billion-year timescales, not when gravity is the only force that matters. The collision between the Milky Way and Andromeda has no winner. Neither galaxy survives, neither dominates, neither imposes its will on the other. Both are destroyed as separate entities, their structures erased, their identities dissolved, their forms transformed beyond recognition. And yet, and this is the part that takes some sitting with, that's not really defeat either, because the substance persists, the stars continue, the mass endures. What's destroyed is pattern, organization, structure, identity. But matter itself, that just rearranges following physics, finding new configurations, building something new from the pieces of what was. Let's talk about what actually happens to the stars during the merger, because there's a common misconception that needs addressing. When people hear galactic collision, they often imagine stars smashing into each other, planets destroyed, solar systems obliterated in cosmic violence, explosive chaos on an unimaginable scale. But the reality is far less dramatic and far more strange. Space is mostly empty, astonishingly, almost incomprehensibly empty. If you took the sun and shrank it down to the size of a period at the end of a sentence, the nearest star, Proxima Centauri, would be about 11 kilometers away. That's the scale we're talking about. Tiny objects separated by enormous distances. A galaxy, isn't a densely packed collection of stars. It's a vast emptiness with occasional points of light scattered through it. When two galaxies collide, when hundreds of billions of stars from each galaxy pass through the region occupied by the other galaxy, the odds of any two stars actually hitting each other are vanishingly small. Imagine two swarms of gnats flying through each other. Each gnat would pass through the opposite swarm without touching any other gnat, because the space between gnats is so much larger than the gnats themselves. That's what happens with stars during galactic mergers. Computer simulations tracking individual stellar motions during mergers consistently show the same result. Maybe a few hundred stars out of hundreds of billions will experience direct collisions. That's statistically negligible, essentially zero. The vast majority of stars, 99.9999% or more, will pass through the merger without ever coming close to another star. They'll have their orbits completely disrupted by the changing gravitational field. They'll be flung onto new trajectories, scattered into different regions of the merged galaxy, possibly ejected from the system entirely. But actual collisions? Rare enough to be ignored. Our own sun, if it still existed during the merger, which it won't because it will have died about 5 billion years from now, while the merger happens 10 to 11 billion years from now, would almost certainly pass through the entire event without encountering another star. It would find itself on a new orbit around Milkomeda's center, possibly farther from the core than its current orbit, possibly closer, possibly ejected from the galaxy entirely to wander alone through intergalactic space. But collision? The probability is so low it's not worth calculating. This means that any planets orbiting stars, assuming they've survived their own star's evolution through red giant phase or whatever other catastrophes billions of years of stellar aging produce, would also survive the merger. Not necessarily in habitable form, not necessarily in configurations that would support life, but physically intact, still orbiting their stars, still following the same local dynamics they followed before, even while their position in the larger galaxy changes completely. There's something both comforting and unsettling about that, isn't it? The idea that the most dramatic event in our galaxy's future, the collision that will transform everything, will also somehow pass harmlessly by most of the actual objects in both galaxies. The destruction is structural rather than physical. It's the death of organization while substance continues. The end of pattern while matter persists. For our solar system specifically, assuming it somehow survived until the merger, which again it won't because the sun will consume the inner planets during its red giant phase, the odds are roughly 50-50 whether it would remain bound to Milkomeda or be ejected into intergalactic space. Computer simulations show that about half the stars in both galaxies end up in the merged galaxy, while the other half get flung out during the collision, given enough energy by gravitational interactions to escape the merged system entirely. If ejected, the sun and its remaining planets would become intergalactic wanderers, drifting through the void between galaxy clusters, no longer part of any galaxy, isolated from the structures that gave them birth. The night sky from such a world, assuming anyone or anything was there to see it, would be profoundly dark. No Milky Way band across the sky because you're no longer in a galaxy. Just a few distant smudges that are other galaxies millions or billions of light years away, and otherwise darkness. Deep, profound, existential darkness. The loneliest possible position in the universe, cast out from home, drifting in the void, isolated from everything. If retained, the sun would find itself on a new orbit in Milkomeda, possibly in the central regions where star density is higher, possibly in the outer halo where stars are more spread out. The night sky would be different. No spiral structure to see from within because Milkomeda is an elliptical. just a generally higher or lower background glow depending on your position relative to the galactic centre. Different constellations as nearby stars move onto different orbits, different neighbours, different context, same star, same planets, just in a completely different cosmic neighbourhood. But of course, none of this matters for Earth or for humanity, because we'll be gone long before any of it happens. The Sun will swell into a red giant in about 5 billion years, probably consuming Mercury and Venus, and rendering Earth uninhabitable long before it actually engulfs our planet. By the time first contact happens 4 billion years from now, the Sun will already be entering its red giant phase. By the time the merger completes 10 or 11 billion years from now, the Sun will have been a white dwarf, a cooling stellar corpse, for billions of years. Life on Earth has maybe 1 billion years left, possibly less, before the Sun's increasing luminosity makes the oceans boil and the atmosphere escape and the planet becomes a sterile, dead rock. Everything that happens after that, the red giant phase, the planetary nebula, the white dwarf cooling, the galactic merger, happens in a universe without us, without Earth as we know it, without any of the biological or cultural heritage of humanity, except perhaps in whatever form might have escaped to other star systems or persisted in ways we can't currently imagine. There's a Zen koan, one of those paradoxical questions meant to break logical thinking and force insight, that asks, what is the sound of one hand clapping? The point isn't to find a clever answer, it's to recognize that the question itself reveals the limitations of dualistic thinking. Clapping requires 2 hands. Asking about one hand clapping is asking about something that exists outside the categories we normally use. In that spirit, what is the sound of one galaxy colliding? What does victory mean when both combatants are destroyed? What does losing mean when the substance persists? What does winning mean when identity dissolves? The questions assume categories, winner and loser, victor and vanquished, that don't apply to cosmic transformations. Both galaxies lose their identities. Neither survives as it was. And yet, in a deeper sense, nothing is truly lost except temporary patterns, transient forms, impermanent structures. Buddhist philosophy talks about the death of ego, the recognition that the self we think of as permanent and essential is actually a temporary construct, a pattern of thoughts and memories and habits that arises and passes away like everything else in the universe. Clinging to that sense of permanent self causes suffering. Recognizing its impermanence, accepting the flowing nature of identity, releases you from that suffering. You still exist, still function, still experience, but without the illusion that there's some unchanging essence that defines you. Galaxies don't have egos, don't have consciousness, don't experience suffering, but the principle applies. The Milky Way and Andromeda are temporary patterns, structures that arose from gravitational collapse and dark matter scaffolding and the particular conditions of the early universe, and which will dissolve when those conditions change. The matter persists, the mass continues, but the pattern, the thing we call the Milky Way or Andromeda, is temporary, impermanent, destined to dissolve. Recognizing that doesn't diminish our galaxy, it just places it in context. We're not permanent fixtures of the universe. We're temporary organizations of matter that happen to exist in this particular epoch, under these particular conditions, in this particular form. Eventually, inevitably, those conditions will change, and the form will change with them. That's not defeat. That's just change, transformation, the ordinary operation of physics over cosmic time. Ancient cultures often had concepts of sacred defeat, of losing that leads to something greater. Christ's crucifixion in Christian theology isn't portrayed as defeat, even though it obviously looks like one. It's portrayed as necessary sacrifice that enables resurrection and redemption. Odin, in Norse mythology, hangs himself from the world tree Yggdrasil for 9 days, sacrificing himself to himself, experiencing death to gain wisdom. The hero's journey in countless mythologies involves symbolic death and rebirth, descending into the underworld or facing annihilation before emerging transformed. The merger of the Milky Way and Andromeda follows that pattern. Both must die as separate entities, must lose their spiral structures, must surrender their identities, must accept transformation to become something larger. Not larger in the sense of better or superior, but larger in mass, larger in scope, larger in gravitational significance. Milkomeda will be more massive than either predecessor alone, will exist for longer, will influence its cosmic neighborhood more significantly. The death of both identities enables that larger existence. But here's what makes cosmic transformation different from human sacrifice narratives. There's no consciousness making the choice, no hero accepting their fate, no deliberate sacrifice. The galaxies don't choose to merge. They don't accept their transformation with noble resignation. They just follow physics. Gravity pulls them together. Tidal forces tear them apart. Orbital mechanics dictate the timeline. It all happens with the perfect indifference of mathematical law, without meaning or purpose or intention. And perhaps that's more profound than sacrifice narratives where transformation happens by choice. The universe doesn't need meaning to transform things, doesn't need purpose to create something new from something old, doesn't need consciousness to follow the laws that govern how matter organizes itself over time. The transformation just happens because the mathematics requires it, because initial conditions lead inexorably to final outcomes, because the universe operates according to principles that care nothing for our desires for meaning or narrative or significance. This collision happens constantly throughout the universe, has been happening for billions of years, will continue happening for billions more. Everywhere we look with powerful telescopes, we see galaxies colliding, merging, transforming, the antennae galaxies in mid-merger, the mice galaxies wrapped around each other, the tadpole galaxy with its enormous tidal tail, countless others at various stages of collision and merger, each one following the same basic physics, each one destroying the identities of both participants while creating something new. This is how the universe builds large galaxies, not through patient accretion, not through slow growth, but through merger and collision. Small galaxies form first in the early universe. They collide and merge into larger galaxies. Those larger galaxies collide and merge into even larger ones. Over billions of years, through countless mergers, the universe produces the giant ellipticals we see at the centers of galaxy clusters, massive structures containing trillions of stars, built from the wreckage of dozens or hundreds of smaller galaxies that collided and dissolved their identities into something larger. Milkomeda will be one step in that process. 2 large spirals merging into one large elliptical, which might eventually merge with other galaxies in the local group, which might eventually be absorbed into an even larger structure if the expansion of space doesn't carry everything too far apart first. It's hierarchical, this process of galactic growth. Endless mergers building ever larger structures until the expansion of space finally wins and isolated galaxy groups drift apart into cosmic loneliness. There's no shame in that, no defeat, no losing. Just transformation following inevitable paths, matter rearranging itself according to physical laws. Temporary forms dissolving and new forms emerging. The Milky Way doesn't lose to Andromeda. Andromeda doesn't lose to the Milky Way. Both lose their temporary identities while their substance continues, which isn't really losing at all when you step back far enough to see the larger pattern. The paradox of winning through losing, of gaining through surrender, of becoming something larger by giving up individual identity. These aren't just spiritual concepts or philosophical abstractions. They're literally what happens in galactic mergers, what happens constantly throughout the universe, what will happen to us and our nearest large neighbour over the next 10 billion years. And perhaps there's wisdom in that, a kind of cosmic teaching about impermanence and transformation and the futility of clinging to forms that were always temporary. Not wisdom in the sense of some intelligence trying to teach us something. The universe isn't pedagogical, doesn't care whether we learn anything, but wisdom in the sense of truth revealed through observation, understanding, gained by watching what actually happens when forces play out over cosmic time. We resist transformation because we identify with our current form, our current structure, our current identity. We want permanence, stability, continuation. We build monuments meant to last forever, create institutions meant to persist, establish identities meant to remain unchanged. And then time dissolves them all, transforms them all, reveals them all to be temporary, regardless of our desire for permanence. Galaxies can't resist because galaxies don't have desire. They just follow physics, and perhaps that's the real lesson. Not that we should resist less, though maybe we should, but that transformation happens whether we resist or not. That identity is always temporary, that forms always dissolve, that clinging to permanence causes suffering when permanence is impossible. The Milky Way and Andromeda will become Milkomeda. Both will lose, neither will win. The result will be something new that contains pieces of both while being fundamentally neither. And the universe will continue, building larger structures through merger and collision, transforming temporary forms into new temporary forms, following mathematical laws with perfect consistency and absolute indifference. There are no losers in galactic collisions because losing implies a game with rules and victory conditions, and the universe isn't playing games. There are only participants in transformation, structures dissolving and reforming, matter following gravity's patient pull toward ever larger organizations. Both will be destroyed, both will persist, both will lose their identities while their substance continues, and what emerges will be something. Neither would have become alone, something that requires the dissolution of both to exist, something new and massive and significant that couldn't exist without the transformation of both predecessors. No winners, no losers, just transformation, just change, just the universe being itself, following its own rules, creating new patterns from old patterns, patient and inexorable, and utterly indifferent to our need for narrative closure. Two galaxies became one, both ceased to exist, neither was defeated, something new was born. The matter continues, the story persists, the universe moves forward, ready for whatever comes next in its endless cycle of transformation. So let's return to where we started, to tonight, to right now, to this moment before sleep when you're settling into rest, and the universe continues its patient work around us. The collision we've been tracing through billions of years, following from first approach through multiple violent passes to the birth of Milkomeda, that collision is still far in the future. 4 billion years before first contact, 10 or 11 billion before the merger completes. Timescales so vast they make human history look like a single breath, make our entire species' existence seem like a brief flicker in cosmic terms. We won't see it, won't be here, won't witness any of the spectacular violence we've been imagining together. Humanity will be gone, our sun will be dead, Earth will be uninhabitable or consumed. Everything we know, everything we've built, everything we've loved and lost and created, all of it will have dissolved into the past billions of years before Andromeda and the Milky Way finally merge. And yet, somehow, we know how it ends. We've traced the trajectories, run the simulations, calculated the binding energies and orbital decay rates. We've watched the dance play out in computer models millions of times, seen the multiple passes, witnessed the black holes merge, watched Milkomeda emerge from the wreckage. We know the ending to a story that won't finish for longer than our planet has existed. There's something profound about that, isn't there? This ability to understand futures we'll never inhabit, to trace consequences we'll never experience, to know endings we'll never witness. It's a peculiar gift of intelligence and mathematics, this capacity to extend awareness beyond our own existence, to comprehend patterns that operate on timescales that dwarf our species. The question we started with, which galaxy wins, turns out to have been the wrong question all along. There are no winners in galactic collisions. Both the Milky Way and Andromeda will be destroyed as separate entities, their beautiful spiral structures erased, their identities dissolved, their forms transformed beyond recognition. And yet, both persist in substance, their stars continuing, their mass enduring, just rearranged into something new. Destruction and creation happening simultaneously, ending and beginning wrapped so tightly together you can't really separate them. The violence, when it comes, will be structural rather than physical. Stars almost never collide, even during galactic mergers. The destruction is of pattern and organization, rather than of objects themselves. Form dies while substance continues. Identity ends while matter persists. It's a gentler apocalypse than you might imagine, and somehow more profound for being gentle. The transformation itself is inevitable, written into the mathematics from the beginning, determined by initial conditions and physical law rather than by choice or chance. The gravitational trap was set billions of years ago. The dance has been choreographed since both galaxies formed. The ending is already approaching, has been approaching for longer than Earth has existed, will continue approaching for billions of years more with patient inevitability. But endings aren't always tragic, are they? Sometimes they're just transformative. Sometimes two things must cease to be what they are to become something neither could have been alone. Sometimes losing individual identity enables something larger, something more massive, something that couldn't exist without the dissolution of both predecessors. Milkomeda doesn't exist yet, won't exist for another 10 billion years, but we've named it already, modelled it in our simulations, traced its formation through computer calculations, accepted it as our inevitable future. We know what it will look like, smooth, featureless, massive, slowly aging over trillions of years. We know it will be beautiful in its own way, not with the photogenic beauty of spirals, but with the honest simplicity of structure stripped down to fundamentals, just mass and gravity doing what they do, following physics with perfect consistency. The collision is coming, has been coming for billions of years already, will continue coming long after we're gone. The approach continues tonight, right now, as you settle towards sleep. 110 kilometers per second of mutual attraction, patient and inexorable, building toward a transformation that will take longer than complex life has existed on Earth. There's strange comfort in that, isn't there? In knowing that some processes are so vast, so patient, so utterly beyond human scale, that they make our anxieties seem small by comparison. The collision will happen whether we worry about it or not. The transformation is already written into the trajectories, already determined by masses and distances and orbital parameters. We're passengers on a galactic journey toward merger, and there's nothing to do but appreciate the ride. Tonight, if you step outside and look up at that faint smudge in the autumn sky, at Andromeda, barely visible, requiring dark skies and patience to spot, you'll see it exactly as countless generations before you saw it. Still distant, still faint, still approaching but not yet arrived. It looks peaceful, innocent, unthreatening, just another fuzzy patch among the stars. But now you know what it really is. Not just a neighbouring galaxy, but our partner in a billion-year dance toward merger. Not just something separate out there, but something already touching us through overlapping dark matter halos, already bound to us by gravity that's been building for longer than Earth has existed, already falling toward us with the inevitability of mathematics. You know it's not a question of if, but when, not a possibility, but a certainty, not a distant threat, but an ongoing transformation that's already begun in the invisible architecture surrounding both galaxies. The collision isn't coming. It's here, happening now in the slowest way possible, unfolding across timescales that make human history look like a heartbeat. And you know that when it finally happens, when the visible parts finally crash together, billions of years from now, there will be no winners, no losers, just transformation, just two temporary patterns dissolving and a new pattern emerging, just matter following gravity's patient instructions, rearranging itself according to physical law, creating something new from something old. The universe continues its work around us, patient and indifferent, building and destroying and rebuilding, following laws as simple and elegant as any poem, creating beauty through transformation, finding meaning in mathematics, expressing itself through the slow collision of galaxies across billions of years. Sleep well in the knowledge that some stories are so vast they outlast civilizations, so patient they dwarf species, so inevitable they render worry meaningless. The dance continues, the approach proceeds, and somewhere billions of years in the future, Milkomeda waits to be born from the dissolution of everything we call home. This is the sleepy astronomer, wishing you peaceful dreams in a universe where endings and beginnings blur together, where losing and winning cease to have meaning, where two galaxies fall toward each other through the darkness with perfect patience and inevitable grace. The collision continues, the transformation approaches, and tonight, as always, the cosmos spins on,